So, here's something worth thinking about as you settle in tonight. Right now, at this very moment, somewhere over eastern Ukraine, a machine the size of a dinner plate is hanging in the air above a dark field. It weighs about 2 pounds. It costs about $400. It was assembled by a volunteer in a kitchen from parts ordered online in 3 clicks. And inside that small, cheap, unremarkable machine, something extraordinary is happening. A tiny chip is reading data from a gyroscope 1,000 times per second. Each reading tells the chip which way the machine is tilting. Each tilt triggers a correction. Each correction adjusts the speed of one of 4 tiny electric motors by a fraction of a percent. And each adjustment changes the angle of the machine by a fraction of a degree. 1,000 times a second. Up, down, left, right, faster, slower. The machine is not still. It is never still. What looks like a perfectly stable hover is actually a continuous, furious, silent conversation between a sensor and a motor. A question and an answer, repeated over and over and over, faster than you could blink. That conversation has a name. Engineers call it a feedback loop. And that feedback loop, that simple, elegant, relentless cycle of measure, compute, correct, is the reason that machine can fly, the reason it knows where it is, the reason it can see in the dark, navigate without GPS, dodge a tree branch, find a target, and return home on its own. Every single capability a drone has, from the most basic to the most terrifyingly advanced, grows out of that same seed, that same loop, made more complex, made faster, made smarter, layer by layer, over the course of about 20 years. And that's what I want to talk about tonight. How that loop was built. How it learned to balance, then to navigate, then to see, and finally, in some cases, to make decisions on its own.
How a machine that started as a toy for hobbyists became one of the most rapidly evolving technologies on the planet. A technology that has already changed the way wars are fought and may change a great deal more before it's done. But here's the thing, and this is the part I really want you to sit with. The technology inside that $400 drone hovering over a field in Ukraine is not some exotic military invention. The gyroscope is the same kind that's in your phone right now, lying there next to your pillow. The GPS chip was designed for car navigation systems. The processor is a relative of the one in your laptop. The motor was originally built for model aeroplanes. And the camera? Well, the camera is barely different from the one you used to take a picture of your lunch last Tuesday. Every component, every sensor, every piece of software inside a modern drone was born in the civilian world, in the consumer electronics market, in hobbyist workshops, in university labs.
And that fact, the fact that the building blocks of one of the most consequential weapons of the 21st century are available to anyone with a credit card and a shipping address, is one of the most profound and unsettling developments in the history of technology. So, here are the questions we're going to spend the evening with. How does a drone actually stay in the air? And why was that so much harder to achieve than it sounds? What happens inside those sensors and chips 1,000 times every second that keeps the machine from tumbling out of the sky? How does a drone know where it is when it's half a mile away and 150 feet above the ground? And what happens when that knowledge is taken away? Your phone, the one lying next to your pillow right now, has a gyroscope, an accelerometer, a GPS chip, a camera, and a processor. Every single component a drone needs to fly and navigate and see.
So why does a 2-pound machine made of those same parts now have the power to change the course of a war? How did these machines go from $30,000 prototypes that only institutions could afford to $400 weapons that volunteers build on kitchen tables? And what does it mean for all of us that the barrier between a consumer gadget and a guided munition has essentially disappeared? And where is all of this heading? What happens when the loop gets fast enough and smart enough that it no longer needs a human being in it at all? We're going to take our time. We're going to start with the physics, with the air and the spinning blade and the force that pushes a machine off the ground. And we're going to work our way forward, layer by layer, loop by loop, until we arrive at the present moment, which turns out to be one of the most remarkable and one of the most uncertain moments in the entire history of engineering.
And if that sounds ambitious for a single evening, don't worry. We're going to take our time. We're going to follow the technology the way it actually developed, not as a list of inventions, but as a story. A story about engineers who couldn't get their machines to stop wobbling. About a graduate student in Hong Kong who spent years trying to make a helicopter hover. About hobbyists who built racing drones for fun and then watched, stunned, as their creations became weapons. About soldiers who learned to build guided munitions in their kitchens from parts ordered online. And about the arms race that followed. A race between the people building drones and the people trying to shoot them down. A race that is happening right now, today, with each side adapting to the other in a cycle measured not in years or months, but in days. If you drift off along the way, that's perfectly fine. The loops will keep running without you. Let's start where everything starts, which is with a blade spinning in the air. Because before we can talk about feedback loops and sensors and artificial intelligence, we need to understand a very simple, very old, very physical question. How do you make something heavier than air go up? The answer is something you've felt 1,000 times without thinking about it. Stick your hand out of a car window while it's moving. Angle your palm slightly upward, fingers pointing forward. You'll feel your hand pushed up. That's lift. The moving air hits the tilted surface of your hand and gets deflected downward. And by Newton's third law, your hand gets pushed upward. Equal and opposite reaction. Simple as that. A propeller blade works on exactly the same principle, except instead of moving through the air in a straight line like your hand out the window, it spins. Each blade is shaped with a slight twist and a curved profile, like a tiny airplane wing rotating around a central hub. As it spins, it grabs the air above it and flings it downward. The blade's angle and shape deflect the air, pushing it down, and by Newton's third law, the blade is pushed up. There's a secondary effect too. The curved upper surface of the blade forces air to accelerate as it flows over the top, which lowers the pressure above and raises it below, adding to the lift. For drone propellers, though, the dominant contribution is the direct downward push of air, the momentum transfer. It's not subtle aerodynamics doing most of the work. It's the blade physically shoving air downward, hard and fast. The faster the blade spins, the more air it pushes down, and the more upward force, the more lift it generates. Now, here's the first thing that matters for our story. The amount of lift a spinning propeller produces depends on how fast it's rotating. Spin it slowly, you get a little lift. Spin it fast, you get a lot. And if you can control the speed of that spinning very precisely, you can control the lift very precisely. You can make the machine go up or go down just by making the blade spin a little faster or a little slower. And that brings us to the motor. Because in order to control the speed of a spinning blade with the kind of precision a flying machine needs, you need a motor that can change its speed almost instantly, thousands of times per second, without wearing out, without overheating,
without falling apart. For most of the 20th century, electric motors couldn't do this. Traditional electric motors use small carbon blocks called brushes that press against the spinning part of the motor, the rotor, to deliver electricity to it. The brushes are always in physical contact with the rotor, which means friction, which means heat, which means wear. You can picture it like the lead of a pencil pressing against paper as you write. Eventually, the lead wears down.
And more importantly, at high speeds, those brushes start to spark. The motor gets noisy, gets hot, loses efficiency, and can't maintain the precise speed control you need. The breakthrough came with brushless motors, and this is one of those enabling technologies that rarely gets the attention it deserves. Even though without it, the entire drone revolution simply couldn't have happened. A brushless motor flips the whole design of a traditional motor. Instead of delivering electricity to the spinning part through physical contact, it creates a rotating magnetic field in the stationary outer part, the stator, and that magnetic field pulls the rotor around. The stator has coils of wire arranged around its circumference, and by rapidly switching which coils are energized and in which direction, the controller creates a magnetic field that rotates around the stator, dragging the permanent magnets on the rotor along with it. No brushes touching anything, no friction at the contact point, no sparks. The motor runs cooler, quieter, faster, and lasts much, much longer. Where a brushed motor might wear out after a few hundred hours, a brushless motor can run for tens of thousands. And crucially, its speed can be adjusted with extraordinary precision by an electronic speed controller, a small circuit board, usually called an ESC, that rapidly switches the current flowing to the motor coils hundreds or thousands of times per second. The ESC is essentially a very fast switch, powered by the drone's lithium-ion or lithium polymer battery, and it can change the motor speed in milliseconds. It is this electronic precision, the ability to command a motor to change its RPM by a tiny fraction almost instantaneously, that makes modern drone flight possible. Think about what that means. You now have a motor that can go from 10,000 revolutions per minute to 10,050 revolutions per minute in a fraction of a second, on command, without any mechanical linkage, without any gears, without anything touching anything. Just electrons flowing through copper wire, creating magnetic fields that pull a magnet around in a circle. The precision is electronic, not mechanical. And electronic precision is cheap, fast, and reliable in a way that mechanical precision never was. This matters enormously because of what came next. Because once you have a motor that can precisely and instantly change its speed, you can build a machine with 4 of them, each driving its own propeller, each independently controllable. And that machine is the quadcopter. Now, here's a question that might seem strange. If a quadcopter is such a simple and elegant design, 4 motors, 4 propellers, arranged in a symmetric cross, why wasn't it invented 100 years ago? People certainly tried. There were experimental quadcopter designs as early as the 1920s, but they never worked well, and the reason is beautifully illuminating. A mechanical quadcopter, one powered by a single internal combustion engine driving all 4 propellers through a system of gears and shafts, is a nightmare. The gearbox alone would be heavy, complex, and prone to failure. But the real problem is control. To maneuver a quadcopter, you need to change the relative speeds of the 4 propellers independently and very quickly. With a mechanical drive system, that requires variable ratio gearing or adjustable pitch propeller blades, both of which add enormous weight, complexity, and failure modes. The machine would struggle to get off the ground under the burden of its own control system.
There's another piece of the puzzle that had to fall into place before the quadcopter became practical. And it's easy to overlook because it sits quietly in the belly of the machine, doing nothing dramatic. The battery. Internal combustion engines, for all their drawbacks in a drone application, have one enormous advantage. Fuel is energy dense. A gallon of gasoline contains roughly 120,000 BTUs of energy. A lithium polymer battery of the same weight holds about 30 times less. This is why gasoline-powered vehicles can drive hundreds of miles, while battery electric vehicles struggle to match that range. And for a flying machine, where every gram of weight directly reduces flight time, energy density is everything. The breakthrough that made electric quadcopters practical was the development of high-energy density lithium polymer batteries, or LiPo batteries, driven largely by demand from the laptop and smartphone industries.
These batteries could deliver high current, meaning the motors could draw the bursts of power needed for rapid acceleration and aggressive maneuvering. They could be recharged hundreds of times, and they were light enough, just barely, for a small drone to carry one and still have enough power left over for useful payload and reasonable flight time. Even so, flight times remain short. A typical consumer quadcopter gets 20 to 30 minutes of flight on a fully charged battery. A heavily loaded FPV racing drone might get 5 to 8 minutes. This is the fundamental constraint imposed by battery physics, and it's why a drone pilot counts every minute, why battery management is a constant preoccupation, and why one of the most important features of any drone is its low battery return-to-home behavior. The automated sequence where the drone calculates whether it has enough remaining power to fly back to its launch point, and if so, breaks off whatever it's doing and heads home. But with 4 independent brushless electric motors, each driven by its own electronic speed controller, the problem of mechanical control vanishes. Each motor can be commanded individually, at any speed, at any moment, by a tiny computer sending electronic signals down a wire. No gears, no shafts, no mechanical linkages. The weight penalty is almost nothing. The response time is almost instant. So, let's pause and look at this machine from above. 4 propellers arranged in a cross pattern. 2 of them spin clockwise. The other 2 spin counterclockwise. This is important because it means the rotational forces cancel out. If all 4 propellers spun the same direction, the body of the drone would spin the opposite way, thanks to Newton's third law. By having 2 spin one way and 2 spin the other, the torques balance and the body stays still. No tail rotor needed, which is one of the things that makes a traditional helicopter so mechanically complex.
If all 4 propellers spin at exactly the same speed, the drone generates equal lift at all 4 corners, and it rises straight up. Want it to move forward? Speed up the 2 rear motors slightly and slow down the 2 front motors. The back of the drone lifts a little higher, the front dips, and the whole machine tilts forward. Now the total lift force is angled, pushing the drone both up and forward. Want to rotate in place? Speed up the 2 clockwise spinning motors and slow down the 2 counterclockwise ones. The torques no longer balance, and the drone yaws, turns around its vertical axis. Every movement, every tilt, every turn, every change in altitude comes down to adjusting the relative speeds of those 4 motors. Forward, backward, left, right, up, down, rotation. It's all just motor speed. There are no control surfaces, no ailerons or rudders like on an airplane, no swash plate like on a helicopter. The simplicity is beautiful. 4 motors, 4 numbers.
Adjust those 4 numbers correctly, and the drone can do anything. But that word, correctly, is doing a lot of work in that sentence, because each adjustment has to happen fast, phenomenally fast, because a quadcopter is inherently unstable. Unlike an aeroplane, which has wings that provide passive stability, a quadcopter has no natural tendency to stay level. If a gust of wind tilts it 2 degrees to the left, there's nothing in the physics of the machine that pulls it back to level. It will just keep tilting, faster and faster, until it flips over and crashes. Which means a quadcopter cannot fly on motor power alone. It needs something else. It needs a way to detect that 2-degree tilt the instant it happens, and a way to correct it before the tilt becomes 5 degrees, then 10, then a crash. It needs a sensor. It needs a computer. And it needs a connection between them that runs faster than the physics of falling. It needs, in other words, a feedback loop. And that loop, the one that detects a tilt and corrects it before you can blink, is where the real story of drones begins. Because the motors and propellers are just muscle. The feedback loop is the nervous system. And without it, all you have is 4 spinning blades and a very short, very expensive flight ending in a pile of broken plastic. So, how do you build a nervous system for a machine that has to make 1,000 corrections per second just to stay in the air? To understand how a drone balances, you need to understand 2 small, remarkable sensors. One is called a gyroscope. The other is called an accelerometer. They are typically packaged together on a single chip no bigger than your thumbnail, along with a magnetometer and sometimes a barometer, in a unit called an IMU, an inertial measurement unit. And this tiny chip is, in a very real sense, the drone's inner ear. Start with the gyroscope. Not the big spinning brass wheel you might have played with as a child, but a MEMS gyroscope, which stands for Micro-Electromechanical System. Inside this chip, there's a tiny vibrating structure, sometimes a tuning fork shape, sometimes a vibrating ring, etched into silicon at a scale so small you'd need a microscope to see it. This structure vibrates at a known frequency, like a tuning fork humming at a constant pitch. And here's the clever part. When the chip rotates, the vibrating structure experiences a force called the Coriolis force, which pushes it sideways, perpendicular to both the direction of vibration and the direction of rotation. Tiny capacitive plates around the structure detect this sideways deflection, and from the size of the deflection, the chip calculates how fast it's rotating. The key thing is that a gyroscope measures the rate of rotation, not the angle, not the position, just how quickly the chip is turning around each of its 3 axes. Pitch, which is tipping forward or backward, roll, which is tipping left or right, and yaw, which is rotating around the vertical axis, like spinning in a chair. If the drone is completely still, the gyroscope reads 0 on all 3 axes. If a gust of wind tips the drone 2 degrees to the left, the gyroscope doesn't tell you that the drone is tilted 2 degrees. It tells you that the drone is rotating to the left at some number of degrees per second. As long as the tilt is happening, the gyroscope sees it. The moment the tilting stops, even if the drone is now stuck at a 20-degree angle, the gyroscope goes back to reading 0, because there's no more rotation happening. This is where the accelerometer comes in. An accelerometer measures linear acceleration, the forces acting on the chip. At rest, sitting on a table, an accelerometer reads 1 g downward, the force of gravity. If you tilt the chip, gravity's pull gets distributed across the chip's axes. Some of the 1G force that was purely in the vertical axis now shows up in the horizontal axis. By measuring how gravity's force is distributed across its three axes, the accelerometer can tell you which way is down, which means it can tell you the drone's orientation relative to the ground, its absolute tilt angle. So why do you need both? Because each one has a weakness that the other covers. The gyroscope is fast and responsive, perfect for detecting sudden changes, but it drifts over time. Small errors accumulate. If you relied only on the gyroscope, after a few minutes, it would gradually lose track of which way is truly level, like a compass that slowly points further and further from north. The accelerometer doesn't drift. It always knows which way gravity is pulling, so it always knows which way is down. But it's noisy and sluggish. It picks up every vibration, every bump, every jolt from the motors. And it can't distinguish between gravity and the acceleration of the drone itself. If the drone is accelerating forward, the accelerometer can't easily tell whether that force is from acceleration or from being tilted. The solution is to combine them. And the mathematical tool that combines them is one of the most important algorithms in all of engineering. It was first described in 1960 by a Hungarian-American mathematician named Rudolf Kalman, and it's called the Kalman filter. The Kalman filter is, at its heart, a very smart predictor. Think of it this way. Imagine you're trying to figure out your exact position on a foggy road. You have two sources of information. One is a GPS that gives you a position reading every few seconds, but each reading is off by a random amount, sometimes 30 feet north, sometimes 60 feet south. Noisy, but with no accumulated error. The other is your car's speedometer, which tells you how fast you're going. If you know your speed and direction, you can predict where you should be since the last GPS reading. That prediction is smooth and continuous, but it drifts over time because the speedometer isn't perfectly accurate. What the Kalman filter does is combine these two imperfect sources optimally. It takes the speedometer's smooth prediction and nudges it toward the GPS's noisy but unbiased reading, weighting each source according to how reliable it is at that moment. The result is an estimate of your position that is better than either source alone. Smooth like the speedometer, but accurate over time like the GPS. In a drone, the Kalman filter does the same thing with the gyroscope and the accelerometer. It takes the gyroscope's fast, responsive rotation data to predict where the drone should be oriented right now. And it continuously corrects that prediction using the accelerometer's gravity-based reading of which way is actually down. The result is a smooth, accurate, real-time estimate of the drone's orientation, its pitch, its roll, its yaw, updated 1,000 times per second. And now, here's where the loop closes. Because knowing the orientation is only half the job, the other half is doing something about it. The drone has a target orientation, usually level, unless the pilot is commanding it to tilt for a maneuver. The Kalman filter tells the drone its current orientation. The difference between the target and the current state is the error. And the job of the flight controller is to eliminate that error as quickly and smoothly as possible by adjusting the motor speeds. The algorithm that does this is called a PID controller, which stands for Proportional Integral Derivative. And despite the intimidating name, the idea is simple and beautiful. The proportional part says, the bigger the error, the harder you correct. If the drone is tilted 10 degrees, push hard. If it's tilted 1 degree, push gently. Makes sense, right? But proportional control alone tends to overshoot. You push hard to correct, fly past level, and now you're tilted the other way. So you push back,
fly past again, and you get this oscillation, wobbling back and forth around level without ever settling. The derivative part fixes that. It looks at how fast the error is changing. If the drone is tilted 10 degrees but the tilt is already decreasing rapidly, the derivative term says, ease off, you're already heading in the right direction, don't overshoot. It's like the damping on a car's suspension. It smooths out the correction and prevents oscillation.
The integral part handles a different problem. What if there's a persistent error that the proportional term isn't quite enough to fix? Maybe a slight imbalance in the drone's weight means it always drifts a little to the left. The integral term adds up all the small errors over time and gradually increases the correction until the persistent drift is eliminated. Together, these three terms, proportional, integral, derivative, create a correction signal that is responsive without being jerky, strong without overshooting, and patient enough to eliminate lingering errors. And it all happens so fast, so transparently, that if you watch a well-tuned drone hovering in a breeze, it looks effortless. It looks like it's doing nothing. But it is doing everything, 1,000 times a second, every second. Think about the difference between a bad autopilot and a good one. Some machines jerk during turns, making them sharp and jarring. Others execute turns smoothly, like experienced drivers. That difference is almost entirely down to how well the PID controller is tuned. The quality of a drone's flight, whether it feels smooth and precise or twitchy and nervous, comes down largely to how well the PID gains are calibrated. And this tuning, this careful adjustment of the parameters, is where art meets engineering. There's no single right answer. The best settings depend on the weight of the drone, the size of the propellers, the responsiveness of the motors, even the air temperature and altitude. A set of PID gains that works perfectly for a lightweight racing drone will make a heavy camera drone oscillate wildly. Settings that produce butter-smooth video on a calm day might be too sluggish to handle gusty wind. Getting it right requires testing, crashing, adjusting, and testing again. Many, many times. This is exactly what a young engineer named Wang Tao spent years doing.
In the mid-2000s, Wang was a graduate student at the Hong Kong University of Science and Technology, working under robotics professor Li Zhexiang. His obsession was helicopter flight controllers, the software that keeps unmanned helicopters stable in the air. And what drove him, what kept him in the lab late at night and pulled him out of bed early in the morning, was a specific, maddening challenge: getting an unmanned helicopter to hover. Hovering sounds simple, just stay in one place. But for an unmanned aircraft, it is considered, as Wang himself described it, the pinnacle of autonomous flight systems. Because hovering means every force must be perfectly balanced, every disturbance instantly countered, every gust of wind met with an equal and opposite correction, continuously, indefinitely, without any input from a human pilot. The machine must become its own pilot, running the feedback loop fast enough and accurately enough that it appears to be doing nothing at all.
Wang founded a small company called DJI in 2006 in Shenzhen, initially with the idea of selling flight controllers and components to model aircraft hobbyists. The timing was unfortunate in one sense. Drones at that time were still considered toys, with no real industrial value. And Wang was an inexperienced leader with no clear business strategy. The company lost money. Wang went into debt. His mentor, Professor Li Zhexiang, rescued the venture with personal funds. But Wang kept doing what he did best, which was obsessing over the technology, iterating on the flight control system through version after version, each one a little more stable, a little more reliable, a little better tuned. By 2008, DJI had built a single-rotor helicopter drone with a flight controller that could hover reliably. The third generation of its flight control system represented a genuine breakthrough. It cost about $30,000, and while that sounds expensive, there were buyers, institutions and companies that needed unmanned aerial platforms for surveying, mapping, and aerial photography. What set DJI apart from its competitors wasn't any single breakthrough. It was the attention to detail. Where exactly the sensors were placed on the circuit board to minimize vibration interference. How the Kalman filter parameters were tuned for different airframe sizes. How the PID gains were optimized through thousands of flight hours and crashes. Every time the drone crashed, Wang learned something about how to tune the loop tighter, how to make the corrections faster, how to keep the machine in the air 1 second longer than last time. The drone had 5 key capabilities that set it apart. It had a meaningful payload capacity, about 11 pounds, enough to carry a professional camera or a small package. It had a stabilizing gimbal that reduced vibrations and improved camera stability. It could transmit video wirelessly to the operator. It could hover, that pinnacle of autonomous flight. And it could fly autonomously along pre-programmed waypoints from takeoff to landing, without pilot intervention. How far had DJI progressed by then? In 2008, 3 days after the devastating Sichuan earthquake, Wang flew his drone over the destroyed areas, visiting more than 10 affected counties and capturing over 1,000 photographs that played a role in assessing damage and coordinating recovery. That same year, DJI participated in an all-China drone exhibition alongside military-industrial enterprises and defense research institutes. Even those institutions didn't have many capable drones at the time. As Wang later recalled, from 2008 onward, DJI never had funding problems again. The technology had proved itself, and his thesis, filed at the Hong Kong University of Science and Technology, bore the unglamorous title Automatic Helicopter Control System. It was, in essence, a manual for building the nervous system of a flying machine. Sensors, filters, controllers, feedback. The loop. Wang completed it in 2011 at the age of 31, having juggled graduate studies and entrepreneurship for years. But the knowledge it contained had already been embedded in DJI's products for half a decade. But here's what's really important. Even Wang's impressive $30,000 helicopter was still, fundamentally, just solving one problem: balance. The drone could hover, it could resist wind, it could stay level, but it didn't know where it was. It had no sense of place. Take your hands off the controls, and it would hover beautifully, drifting wherever the wind took it, maintaining its altitude and orientation perfectly, while slowly floating out to sea. To go from a machine that balances to a machine that navigates, the loop needed another layer. It needed to know its position in 3-dimensional space. It needed a sense of place, and that required an entirely different kind of sensor. Imagine standing in a room with your eyes closed. You can feel which way is up thanks to your inner ear, your biological gyroscope and accelerometer. You know you're standing upright. You know if someone pushes you and you start to lean, but you have no idea where in the room you are. You could be in the center, by the door, near the window. Your sense of balance gives you orientation, but not location. To know where you are, you need something external. A sound to orient by, a wall to touch, a landmark to see. A drone with only a gyroscope and accelerometer faces the same problem. It knows which way it's tilted, it knows when it's accelerating,
but it doesn't know its position in the world. If a steady wind pushes it sideways at a constant speed, the accelerometer eventually stops registering the motion because there's no longer any change in velocity. The drone drifts, unaware. The sensor that gives a drone its sense of place is the GPS receiver, and the way GPS works is, when you stop and think about it, quietly remarkable. High above the Earth, at an altitude of about 12,400 miles, a constellation of at least 24 satellites orbits the planet. Each satellite carries an extremely precise atomic clock and continuously broadcasts a signal that includes the satellite's exact position and the exact time the signal was sent. Your GPS receiver, whether it's in a car, a phone, or a drone, picks up these signals from multiple satellites simultaneously and does a simple calculation. If I know when the signal was sent and when I received it, I can figure out how long the signal was in transit.
Since radio signals travel at the speed of light, about 186,000 miles per second, the transit time tells me how far away that satellite is. With the distance to one satellite, I know I'm somewhere on a sphere centered on that satellite. With two satellites, I'm somewhere on the circle where two spheres intersect. With three, I'm at one of 2 points where 3 spheres intersect. And with 4, I have a unique position in 3-dimensional space and a corrected time. The precision is impressive. A civilian GPS receiver can typically determine your position to within about 10 feet. And it does this continuously, usually several times per second, providing a stream of latitude, longitude, and altitude readings. But here's a detail that's easy to overlook and that matters enormously for our story. GPS signals are astonishingly weak. By the time the radio signal from a satellite 12,000 miles away reaches your receiver on the ground, it has spread out over an enormous area and lost almost all of its energy. The received power is something like 10 to the minus 16 watts. To put that in perspective, a household light bulb emits about 60 watts. The GPS signal that your phone is receiving right now is about 1 billion times weaker than the light from a reading lamp across the room. Your GPS receiver is an extraordinarily sensitive radio, pulling meaningful information from a signal so faint that it's buried deep below the background noise of the radio environment. It works because the signals are carefully encoded and the receiver knows what pattern to look for, allowing it to extract the signal from the noise through mathematical correlation. Remember that number, 10 to the minus 16 watts. Because the weakness of that signal is the reason that GPS can be jammed so easily. And the vulnerability of GPS is one of the central dramas of the drone story. Now, combine that GPS position data with the orientation data from the IMU, and you have a drone that knows both where it is and which way it's pointing. Add a barometric altimeter, which measures air pressure to determine height, and a magnetometer, which acts as a digital compass, and you have a remarkably complete picture of the drone's state in 3-dimensional space. DJI's flight controller, by its 4th generation in 2010, called the ACE-1, integrated all of these sensors into a package not much bigger than 2 matchboxes. 2 small black boxes paired with a GPS receiver, and at the time of its release, it was the smallest, lightest, and most stable flight control system available for consumer and commercial drones. It could be installed on virtually any drone platform, whether powered by fuel or electricity, regardless of size or motor count. The key wasn't any single sensor. All of these components, the GPS from U-Blocks, the accelerometers from Freescale Semiconductor, the digital compass from Honeywell, the central processor from ARM, were commercially available, mass-produced, and widely used in smartphones, car navigation systems, and industrial automation. They were off-the-shelf parts. Any competitor could buy the same sensors from the same suppliers. What DJI did, and what set it apart, was integrate them into a flight control system that combined all their data smoothly and reliably through that same Kalman filter we talked about, extended now to handle not just orientation, but position, velocity, and altitude. And critically, all the code was written in-house and kept completely proprietary.
The firmware, the software that ran on the flight controller's processor, was DJI's own, a black box of carefully tuned algorithms representing years of accumulated knowledge about sensor placement, filter parameters, PID gains, and failure modes. This software was the company's true competitive advantage, not the hardware. The hardware was commodity, the intelligence was proprietary. There's an important lesson here about where the sensors sit on the circuit board. It sounds trivial, but sensor placement affects performance significantly. A gyroscope mounted too close to a motor picks up vibration that corrupts its readings. An accelerometer, placed off-center from the drone's center of gravity, introduces errors during rotation. A magnetometer near a power wire picks up electromagnetic interference that throws off the compass heading. DJI's engineers learned these lessons through thousands of crashes, through meticulous testing, through the slow, painstaking process of figuring out exactly where each sensor worked best and how to filter out the noise specific to each mounting location. These details, these mundane-sounding decisions about where to put a chip on a board, were part of what made DJI's products fly better than everyone else's. And with position knowledge came something transformative. The drone could now hold its position, not just its altitude and orientation, but its actual location on the Earth's surface. Activate GPS mode, take your hands off the sticks, and the drone would hover in place, correcting for wind, correcting for drift, locked onto its coordinates like a ship at anchor. If a gust pushed it 10 feet north, the GPS would register the displacement, the flight controller would tilt the drone slightly south, and within seconds, it would fly itself back to its assigned spot.
This is the capability that Wang Tao described as separating his drones from everything else on the market. While competitors struggled just to keep their drones from tumbling, DJI's machines could hover, hold position, and execute pre-programmed flight paths along waypoints, all autonomously. You could tell the drone to fly to coordinate A, then coordinate B, then coordinate C, at a specific altitude and speed, and it would do it without any further human input. Takeoff to landing, fully autonomous in theory, if the waypoints were programmed correctly. And this is where the consumer revolution began. In 2013, DJI released the Phantom 1, a small white quadcopter that could hover, hold position, and fly back to its takeoff point at the push of a button, and it cost about $1,000. That price point was revolutionary. Previous drones with comparable capabilities had cost 10 or 20 times as much.
The Phantom 1 wasn't built with exotic military components. It used the same brushless motors, the same lithium-ion batteries, the same GPS chips, the same MEMS sensors that were flooding out of the consumer electronics industry, driven by the insatiable global demand for smartphones, tablets, and laptops. Shenzhen, the vast manufacturing hub in southern China where DJI was based, was the epicenter of this supply chain, a place where you could source every component you needed for a drone from factories within a few hours' drive, at prices that dropped steadily year after year as production volumes climbed. DJI's success wasn't just technological. An American named Colin Gwynn, a reality TV personality and aerial photography entrepreneur, became the company's North American partner and brought DJI's products to the English-speaking world with the salesmanship and visibility that Wang Tao, focused on engineering, could never have provided alone. Americans bought Phantoms without even knowing DJI was a Chinese company. They just knew the brand. The partnership eventually collapsed acrimoniously, over a dispute about profit sharing with GoPro, whose cameras the Phantom carried. But by then, DJI's dominance was secure. When the partnership ended, Wang didn't look for a new camera partner. He built his own 4K camera, integrated it with a gimbal into the Phantom 3, and from that point on, there were no third-party components in DJI's core product line. Everything was proprietary. Everything was in-house. $1,000. Think about what that number meant. Previous drones with comparable capabilities, the ability to hover, hold position, and fly back to their takeoff point, cost $10,000 to $20,000 or more. The Phantom 1 wasn't just a new product. It was a price point that blew the door open. Photographers could afford it. Filmmakers could afford it. Real estate agents could afford it.
Farmers checking their fields could afford it. Search and rescue teams could afford it. Hobbyists who just wanted to see what their neighborhood looked like from 200 feet up could afford it. The Phantom's timing was also perfect. It arrived just as social media was exploding with visual content, just as YouTube and Instagram were creating insatiable demand for striking aerial footage. Suddenly, the sky was full of small, buzzing, remarkably capable machines, seeing the world from above in ways that had previously required a helicopter and a crew at thousands of dollars per day. And the footage was stunning. Sweeping shots over coastlines, tracking shots through forests, reveal shots over mountain ridges, all captured by a machine that fit in a backpack and launched from a park bench. The story of how DJI transitioned from single-rotor helicopters to quadcopters is itself a lesson in how technology evolves through unexpected channels.
Wang Tao had an unexpected discovery through one of his distributors in New Zealand, where the most popular product wasn't DJI's flight controllers at all, but their camera stabilizers. Customers were buying stabilizers in large quantities to mount on quadcopters, a platform that Wang hadn't been focused on. He investigated and discovered that compared to single-rotor helicopters, quadcopters were easier to operate, significantly cheaper, and, thanks to the rapid development of brushless motors and lithium batteries, increasingly capable. The consumer market was moving toward multi-rotor, and DJI followed. The transition was remarkably fast. In about 6 months, DJI's 5th-generation flight control system was adapted to manage drones with 4, 6, or 8 propellers. The same Kalman filter, the same PID controller, the same sensor fusion architecture that had been developed for helicopters worked for quadcopters with relatively straightforward modifications.
While competitors were still struggling to achieve stable hovering on their multi-rotor platforms, DJI's machines could hover, navigate waypoints, and return home automatically. The years of painstaking tuning on the helicopter platform, all those crashes and adjustments and late nights in the lab, had produced a flight control system so robust that it adapted to an entirely new airframe type in months. But there was a limitation that the Phantom 1 made painfully obvious. It could fly, it could navigate, it could hold position, but it was essentially blind. It had no obstacle sensing, no way to see a tree, a building, a power line. The pilot on the ground was the eyes, and the pilot was looking through a radio link at a live video feed from the drone's camera, trying to navigate a machine that might be 1,000 feet away, moving at 40 or 50 miles per hour, through a three-dimensional environment that the pilot could only see from the drone's single forward-facing perspective. Which meant crashes. Lots of them. Hobbyists hit trees. Filmmakers hit buildings. Beginners flew into their own faces. The drone could balance, it could navigate, but it couldn't see. And to see, the loop needed another layer still. It needed a camera that didn't just record images for a human to watch later, but that fed visual information back into the flight controller in real time, giving the machine something it had never had before:
awareness of its surroundings. The loop was about to learn to see. The first kind of seeing was the simplest, looking down.
DJI's consumer drones, starting with the Phantom series, began incorporating downward-facing optical sensors, essentially small cameras and sometimes ultrasonic rangefinders pointed at the ground. These sensors measured the distance to the surface below and tracked the visual texture of the ground, the pattern of grass or concrete or gravel, to detect lateral drift. If the drone moved sideways, the ground pattern shifted in the camera's view, and the flight controller could detect and correct the drift even indoors, where GPS signals don't reach. This was a modest beginning, but it introduced a crucial principle. The camera was no longer just a passive observer recording footage for a human. It was part of the loop. It was feeding data back into the flight controller, influencing motor speeds, affecting the drone's behavior. The camera had become a sensor. The next step was looking forward. By the mid-2010s, DJI and other manufacturers began adding forward-facing obstacle detection, using pairs of cameras in a stereo configuration, which is just a fancy way of saying two cameras spaced a few inches apart, mimicking human binocular vision. By comparing the images from the two cameras, the software could estimate the distance to objects in front of the drone. If the drone was flying toward a wall, the stereo cameras would detect the wall at a distance of 10 or 15 feet, and the flight controller would slow the drone down. Not stop it necessarily, at least not in the early implementations. There's a telling moment in one of the DJI FPV drone reviews where the pilot flies the drone in normal mode directly at a folding chair, full stick forward, and the obstacle avoidance slows the drone significantly, but doesn't prevent the collision entirely. The drone bumps the chair, the propellers stop, and the pilot inspects the bent wingtips, notes the minor damage, and takes off again. This kind of obstacle response, slowing down rather than stopping or dodging, was characteristic of the early implementations. The drone could see the obstacle, but its repertoire of responses was limited. It was more obstacle awareness than true obstacle avoidance. But even this limited vision was transformative for pilots. It meant that a beginner flying in normal mode had a safety net. The drone wouldn't fly full speed into a wall. It would slow down, giving the pilot time to react. And it meant that in return to home mode, the drone could detect and navigate around obstacles on its path back to the landing point, at least within the field of view of its sensors. Now, there's a different kind of seeing that matters enormously in the drone world, and it's not about the drone seeing for itself. It's about the pilot seeing through the drone. This is FPV, first-person view, and it's worth spending a moment on, because it changes everything about the experience and the capability of flying. In a standard drone setup, the pilot looks at the drone from the ground or at a screen on the controller, showing a live video feed. But in FPV, the pilot wears goggles, a headset with two small screens inside, one for each eye, displaying a real-time video feed from the drone's camera. Look left, and you see what the drone sees to the left. Look down, and you see the ground rushing beneath the drone. The experience is immersive, visceral. Pilots describe it as being inside the machine, seeing the world from the drone's perspective. You're no longer operating a remote aircraft, you're flying. But before we get to FPV, there's another piece of the vision story that matters enormously, and it connects back to our feedback loop in a beautiful way. It's the gimbal. A camera mounted rigidly to a drone would produce unwatchable footage. Every vibration from the motors, every tilt during a maneuver, every gust of wind would jolt the image. To get smooth, cinematic aerial video, the camera needs to be isolated from the drone's movements, stabilized on its own independent platform. That platform is the gimbal, and DJI's breakthrough in this area is one of the key reasons the company came to dominate the market. In January 2012, at the Toy Fair in Nuremberg, Germany, DJI introduced the Zenmuse Z15, the world's first brushless direct drive stabilized gimbal for aerial photography. The Zenmuse used 3 brushless motors, one for each axis of rotation, pitch, roll, and yaw, controlled by their own IMU and their own PID controller. The gimbal was, in effect, a drone within a drone. It had its own gyroscopes, its own accelerometers, its own feedback loop, running independently of the drone's flight controller.
When the drone tilted forward to fly, the gimbal's motors rotated the camera backward by exactly the same amount, keeping the camera level. When the drone rocked in turbulence, the gimbal absorbed the motion. The camera floated, serene and steady, while the airframe bounced around it. The Zenmuse was an instant hit. Starting at about $2,000, it was a fraction of the cost of the helicopter-mounted stabilization systems used in professional filmmaking, which could run to hundreds of thousands. In 2012 alone, Zenmuse sales drove DJI's revenue past hundreds of millions of yuan. By 2013, DJI's 6-rotor S800 drone, equipped with a Zenmuse gimbal, had nearly monopolized the drone market for Hollywood film production. Aerial shots that once required a helicopter and a crew at $6,000 or $7,000 per day could now be captured by a single operator with a drone costing a few $1,000s total.
And here's the connection to our feedback loop. The gimbal is a feedback loop stabilizing a camera. The flight controller is a feedback loop stabilizing the drone. They run simultaneously, independently, nested one inside the other. The drone bounces, the gimbal absorbs. The gimbal stays level, the camera stays smooth. Loop within a loop, layer upon layer. Now let's talk about FPV. FPV began in the hobby world, in a subculture of drone racing, where pilots flew small, fast quadcopters through obstacle courses, wearing goggles, competing for speed and precision. The drones were tiny, fast, agile, and the whole point was the thrill of flight. Pilots raced through parking garages, through warehouse corridors, around pylons in open fields, pushing the machines to their limits, crashing, rebuilding, and crashing again. The FPV racing community developed its own culture, its own jargon, its own celebrities. And in the process, it drove the development of faster, lighter, more responsive quadcopter frames, better FPV cameras with lower latency, and cheaper, more reliable video transmission systems. All of the technology that would later make FPV drones so effective as weapons was incubated in this hobbyist community. Optimized not for lethality, but for fun. You can hear the exhilaration in the voice of someone who has just tried a DJI FPV motion controller for the first time, a handheld wand that you tilt and point to direct the drone. Oh, this is so neat. It's like a whole nother experience. You just point wherever you want to look, and if you pull the trigger, it'll just come right down at you. Full blast. This is really neat. The motion controller turns flying into something intuitive, almost physical. Tilt your hand down, the drone dives. Point at the sky, it climbs. Twist left, it turns. The feedback loop now includes the pilot's own body, their sense of balance and motion translated directly into the drone's flight path. But here's where the story takes its darker turn. Because those same qualities that made FPV racing thrilling, the speed, the agility, the first-person perspective, the ability to thread a needle between obstacles, made FPV drones devastatingly effective as weapons. About a year into the war in Ukraine, a British-born volunteer fighting for the Ukrainian army described the moment of realization. These FPV drones, they came from a hobby called drone racing. There's these relatively small but very fast drones that just see through a kind of little tunnel vision camera, and you're racing them around a course. About a year into the war, people realized that these things not only could go very fast, but could also carry quite some weight. Cable tie an explosive charge to the bottom of a racing drone. Add a simple detonation mechanism, and you have a guided munition. One that costs $400 to $500. One that a soldier with FPV goggles can steer directly into a vehicle, a bunker, or a trench from a couple of miles away. One that can follow a target around a corner, circle back, and come at it from another direction. I've had an FPV come after me a couple of times, and it's terrifying, the same soldier said. Mortars don't even make my heart rate go up. These bastard things can follow you around a corner. You know, they can follow you around one corner and round another, pull a circle, and come at you from the other way. The only defences against an incoming FPV, he explained, are environmental. Tall trees, areas where there's lots of overhead wires, buildings, ideally buildings with nice, robust concrete ceilings.
30 centimeters, about a foot, of Soviet-era concrete above your head is what you want above you, ideally. The drone can't penetrate it. In the open, without overhead cover, there's no real running from it, and there's no real hiding from it. It's either going to kill you, or it's going to miss. The psychological impact is enormous. At first I dreamed a lot about drones, one Ukrainian soldier recovering from wounds in the Netherlands recalled. I was totally convinced that a drone was heading my way. That was early on. Scary. Another described the impossibility of the situation. You have practically no time to look up during the fighting. Bullets are everywhere. And then there's drones. There's not enough time to see everything. The number of drones is extreme, really a crazy amount. It's impossible to hide from them. All you can do is hope it misses you, or it sees you. Alongside the small FPV kamikazes, there are larger drones carrying heavier payloads.
Some of these began as agricultural sprayers, designed to fly over fields, distributing pesticide. In wartime, they've been repurposed to carry multiple explosive charges, weighing several pounds each. Ukrainian soldiers have nicknamed one type Baba Yaga, after the witch of Slavic folklore. Huge, isn't it? A soldier said, examining one. Massive thing. It can carry about 22 pounds long distance and over 40 pounds short distance. These heavy-lift drones can demolish buildings, destroy trenches, and take out vehicles. Before the war, they sprayed fields with pesticide. Now, they help with national defense. The transformation from farm equipment to weapon system required almost no engineering change, just different cargo. And then there are the observation drones, the ones that don't carry explosives, but carry something arguably more powerful: eyes. The DJI Mavic, originally designed for consumer photography, became the backbone of battlefield reconnaissance.
With this, you can see like an eagle from anywhere, the soldier explained. And at night with a thermal camera, it doesn't matter if you're hiding under the foliage, we can see you anyway. Thermal cameras, infrared sensors that detect heat rather than visible light, added another dimension to the drone's vision. A person hiding in a trench, invisible to the naked eye, is a bright, warm spot on a thermal camera. A vehicle that's been running recently is a heat signature that stands out against the cold ground. Even a chimney emitting heat from a fire inside an otherwise empty building becomes visible. As one German reconnaissance specialist put it, reviewing imagery from the Heron TP drone, you can now recognize people, hairstyles, everything. You can even see when people are moving under trees. You can see into the shadows perfectly. You no longer have any blind spots. The combination of these two types of drones, the observation drone and the FPV strike drone, working together created a new kind of warfare. The Mavic pilot finds the target from altitude, watching through a thermal or optical camera. The FPV pilot, sitting nearby in a trench or a basement, launches a strike drone. The Mavic pilot guides the FPV toward the target, providing a bird's-eye view, while the FPV pilot sees through the drone's tunnel vision camera. Two loops cooperating, one seeing the big picture, the other delivering the strike. Most of the time, the FPV pilot is working in conjunction with a Mavic pilot, the soldier explained. The Mavic pilot will find the target, the FPV will launch, and working together, they will guide the FPV into the target. It's literally the most cost-effective way of destroying the enemy at long distance. The larger surveillance drones push the concept even further. Germany's Heron TP, a drone with a wingspan of about 85 feet, can stay airborne for hours, carrying 5 sensors and cameras, including a microwave radar that penetrates cloud cover. When German reconnaissance specialists analyzed its imagery, the leap in capability was immediately apparent. With the old sensors, we were roughly at the level of analog television, one analyst said. Now, with the new sensor technology, we have finally arrived at full HD. We can really say he's holding a cell phone, lighting a cigarette. Depending on whether comprehensive characteristics are known, we might even be able to say which person this really is. The battlefield was becoming transparent. The loop had learned to see, and what it saw was everything. But if the drone can see everything, then the question becomes, can you blind it? Can you sever the links that connect the drone to its pilot, confuse the signals that tell it where it is, disrupt the feedback loop that keeps it flying? Can you, in other words, break the loop? Before we talk about how the loop can be broken, it's worth pausing to note how the military world arrived at this moment. Because drones didn't start as cheap, disposable weapons built in kitchens. They started as large, expensive, and very much controlled by humans. At the turn of the millennium, the US Predator drone represented the state of the art. It was a large, fixed-wing aircraft that could stay airborne for 24 hours, fly thousands of miles, and transmit live video back to operators sitting in air-conditioned trailers in Nevada, thousands of miles from the battlefield. After September 11, 2001, the Predator was armed with Hellfire missiles and began conducting strikes in Afghanistan, Pakistan, and elsewhere. It was the beginning of the age of combat drones and of the debates about unmanned warfare from the sky. But the Predator was not autonomous. It was remotely piloted, with a crew of several operators who flew it, aimed its cameras, designated targets, and launched its missiles. It communicated with its operators through satellite links, and those links were its lifeline. The drone was an extension of the pilot's senses and intentions, separated by distance but connected by radio. The human was always in the loop, making every significant decision. The Ukraine conflict changed this paradigm, not through one dramatic technological leap, but through a million small innovations, driven by necessity, accessibility, and the brutal Darwinian pressure of combat. Suddenly, drones weren't expensive platforms operated by specialist crews from distant bases. They were cheap, ubiquitous, operated by infantry soldiers in the field, and evolving at a pace that no centralized procurement process could match. The technology democratized.
And with that democratization came vulnerability, because the cheap, accessible drones that flooded the battlefield depended on the same fragile, jammable radio links that every other electronic system used. So let's talk about what a drone actually needs, in terms of invisible signals flowing through the air to do its job. Because understanding these signals is the key to understanding how a drone can be attacked and how it can be defended. A typical military or modified civilian drone relies on at least 3 separate radio links, 3 different conversations happening simultaneously between the drone, its pilot, and the sky above. The first is the control link. This is the radio connection between the pilot's controller and the drone. When the pilot moves a joystick or tilts a motion controller, that command is transmitted as a radio signal on a specific frequency, picked up by a receiver on the drone, and translated into motor commands by the flight controller.
If this link is lost, the pilot can no longer control the drone. This is the leash. The second is the video link. In FPV flying, the drone's camera feed is transmitted back to the pilot's goggles or screen in real time, usually on a different frequency from the control link, often in the 2.4 or 5.8 GHz band. If this link is lost, the pilot can no longer see through the drone's eyes. They're flying blind. The third is GPS. The drone is constantly receiving signals from satellites overhead, using them to calculate its position. If these signals are lost or corrupted, the drone no longer knows where it is. The GPS-dependent features, position hold, waypoint navigation, return to home, all stop working. Now, each of these links is a vulnerability, and electronic warfare, the practice of disrupting an enemy's electronic systems, exploits these vulnerabilities with ruthless efficiency. The simplest attack is jamming.
A jammer is essentially a powerful radio transmitter that broadcasts noise, random electromagnetic energy, on the same frequencies the drone uses. If the jammer is powerful enough and close enough, it drowns out the real signals. The pilot's commands can't get through. The video feed dissolves into static. The drone can't hear its controller anymore. What happens next depends on the drone's programming. A well-designed drone, when it loses contact with its controller, doesn't just fall out of the sky. It has a fail-safe, usually return to home. The flight controller detects the loss of the control signal, switches to autonomous mode, looks up the GPS coordinates of its takeoff point, and flies itself back. For consumer drones like the DJI series, this is standard behavior. The drone records its GPS position at takeoff, stores it in memory, and if the control link is lost for a preset number of seconds, it automatically ascends to a safe altitude, orients itself toward the stored home point, and flies back. The pilot of the DJI FPV drone noted this feature with approval. You can go exploring through valleys and stuff, and even if it loses connection, it will come back. Even if it drops connection, not only pushing the return to home. The same pilot demonstrated the low battery return to home function, showing how the drone automatically breaks off from whatever it's doing when the battery drops below a critical level, centers its camera, climbs to a safe altitude, and flies itself home, overriding the pilot's controls until it lands safely. "It just cut me out of control, and it's going to fly back," he narrated as the drone took over. Even the landing accuracy was tested. The first return, from a short flight around a park, landed within 2 feet of the takeoff pad. The second, after a longer flight the greater distance, was off by about 5 feet. Close enough to be useful, not precise enough for a pinpoint landing. But a jammer that can block the control link can often block GPS as well, because GPS signals are remarkably weak, having traveled 12,000 miles from space. They arrive at the receiver with about the same power as a light bulb seen from 12,000 miles away. A modest jammer on the ground can overwhelm that whisper of a signal. GPS denial is already a standard feature of the electronic battlefield, but the impact varies enormously depending on the type of drone. A small FPV drone operating within line of sight of its pilot may not need GPS at all. The pilot is steering by hand through the camera feed. Jam the GPS on an FPV strike drone and the pilot barely notices, because they were never using GPS in the first place. But jam the GPS on a long-range autonomous drone, one that was relying on satellite navigation to fly hundreds or thousands of miles to its target, and the effect can be devastating. This distinction matters because some of the most feared drones in the Ukraine conflict are long-range autonomous systems. The Iranian-made Shahed 136, which Russia mass produces under the name Garan 21, can fly over 1,200 miles and carries an explosive payload with roughly 3 times the power of a standard artillery shell. It navigates primarily by GPS, following pre-programmed waypoints to its target. And that GPS dependency is a vulnerability that the defenders have learned to exploit. There's an even more insidious technique called GPS spoofing. Instead of drowning out the GPS signal with noise, a spoofer transmits fake GPS signals that look legitimate but contain false position data. The drone's GPS receiver picks up the fake signals, trusts them because they have the right format and timing, and calculates a position that is wrong. The drone thinks it's somewhere it isn't. Its navigation goes haywire. On several occasions during the war in Ukraine, defenders successfully spoofed incoming Iranian-made Shahed drones, overriding their GPS target data and sending them off course, in some cases redirecting them toward Russian or Belarusian territory. The drone's loop was intact and running perfectly. It just had the wrong information. So now the picture starts to look grim for the drone. Jam the control link and the pilot loses control. Jam the GPS and the drone loses its sense of place. Spoof the GPS and the drone flies to the wrong location.
All 3 attacks require nothing more than a sufficiently powerful radio transmitter and knowledge of the frequencies involved. And every unit on the modern battlefield has jammers. As one Ukrainian soldier explained, all the brigades have jammers to mess up the drone's radio frequency. You only turn it on when you see a drone. The battlefield environment in eastern Ukraine gives a vivid picture of what this looks like in practice. As one Ukrainian soldier described his daily reality, at the front you're attacked by lots of drones depending on the time of day. At night, there are drones with thermal cameras. Then you have a period when dawn breaks. They change the night drones for day drones. The changeover period takes roughly 90 minutes. Most of the time, the sky is filled with drones. In response, every unit has jammers. We usually have them on the vehicles that take us to our positions. You only turn it on when you see a drone. The jammers are crude but effective against basic drones. They flood the radio spectrum with noise, breaking the control link and often the GPS as well. But the more advanced drones are designed to cope. Some switch frequencies automatically when one channel is jammed, hopping across the spectrum faster than the jammer can follow. Some use spread spectrum techniques that distribute their signal across a wide band, making it harder to jam without blanketing the entire electromagnetic spectrum. And some, as we'll see, don't use radio at all. This is the moment where the loop breaks. The drone is flying, its motors are spinning, its gyroscope and accelerometer are working fine, its PID controller is keeping it level. But the links to the outside world, the control signal from the pilot, the position data from the GPS satellites, are severed. The drone is like a person in that dark room with their eyes closed and their ears plugged. They can stand upright. They can feel which way is up, but they have no idea where they are or where they're supposed to go. And here is where the story could have ended. Drones are effective but jammable, useful but defeatable. The loop is vulnerable at its information links. Case closed. Except that's not what happened. Because the engineers and soldiers and garage tinkerers working on drones looked at this vulnerability and asked a question that changed everything. What if the drone didn't need those external signals at all? What if the loop could close on its own, using only what the drone could see and sense for itself? The loop was about to fight back. The first and most straightforward defense against jamming is also the oldest. Don't use radio at all. During the war in Ukraine, a startling discovery was made when a Russian drone was recovered with a 30-foot cable attached to it. A physical wire trailing from the drone back to the operator. It was a fiber optic cable, a thin glass filament that carries data as pulses of light rather than radio waves. And you cannot jam light inside a glass fiber. There's no frequency to block, no signal to overwhelm, no electromagnetic radiation leaking out for a direction-finding system to detect. The drone communicates with its operator through a physical connection that is invisible to every electronic warfare system on the battlefield. The idea is not new. Wire-guided missiles have existed since the 1950s. The famous Milan anti-tank missile, deployed by NATO forces for decades, trailed a thin copper wire behind it as it flew, with the operator's commands traveling down the wire to the missile's guidance system. What's new is applying this old principle to drones, which need to fly further, maneuver more freely, and transmit high-bandwidth video data, not just simple steering commands.
Fiber optic is ideal for this because it can carry enormous amounts of data, enough for a high-definition video feed, over distances of 12 miles or more without signal degradation, and it weighs almost nothing. A spool of optical fiber thin enough to trail behind a small drone can easily be carried on board. Fiber optic drones solved the jamming problem for control and video links, and both Russian and Ukrainian forces developed them. By some accounts, Russian forces achieved a significant lead in this particular technology, fielding fiber optic FPV drones before Ukrainian forces had widely adopted them. One Russian military analyst described the advantage. Our fiber optic drones, the ones with auto-targeting, what Ukraine still has only in early stages, we already have working. The cable also has the advantage of being effectively invisible to electronic warfare detection systems, since there's no radio emission to intercept. But the fiber has limitations. Ukrainian forces developed creative counters, including launching fiber optic drones from unmanned boats, allowing the drone to operate over water where there are no obstacles to snag the cable. As one analyst explained, they bring launch containers on boats that reach the shore, release the drone, and it flies 12 miles on the fiber. Over rivers, though, the fiber can be dragged by currents and snapped, which limits its tactical use in certain terrain. The cable also restricts the drone's range to the length of the fiber on the spool, typically 6 to 12 miles. The cable can snag on obstacles, and it restricts the drone's range to the length of the fiber on the spool. It works well for tactical strikes within 6 to 12 miles, but it's not a solution for long-range autonomous missions. For those, a different approach was needed. And this is where the loop truly evolved. Because the answer was to give the drone a new kind of sense that it could use even when GPS was gone and radio was jammed. The answer was to teach the drone to see its way home. Visual navigation works on a principle that is, when you hear it, almost elegant in its simplicity. The drone carries a camera pointing downward or forward. It also carries a stored map, a satellite image of the area sourced from Google Maps or a military mapping database. As the drone flies, it continuously compares what its camera sees with the stored map. When it finds a match, it knows where it is. Think about how you navigate an unfamiliar city without your phone. You look at the buildings, the street layout, the parks, the rivers, and you compare what you see with the mental image you have from studying a map before your trip. If you spot a distinctive cathedral that you saw on the map, you immediately know your location. The drone does the same thing, but much faster and more precisely. Using image recognition algorithms to match features in the camera's view. Rooftops, roads, field boundaries, rivers, with the same features on the stored map. The software team at Quantum Systems, the Bavarian company that manufactures the vector reconnaissance drone, developed a system called Receptor AI that does exactly this. If the drone loses its GPS connection, the AI compares the images from the drone's camera with stored maps and calculates the drone's position. The system works in daylight, matching visual features. But at night, the camera sees infrared rather than visible light, and matching infrared imagery to conventional maps presents a different challenge. Because things look fundamentally different in the infrared spectrum. That's an additional technical hurdle for us, the company's engineers acknowledged. To implement visual navigation on the basis of infrared data. But the underlying principle is the same. The drone looks at the world, compares what it sees with what it knows, and figures out where it is. No GPS required. No radio signals from space. Just a camera, a map, and an algorithm. There's a deeper version of this same idea that doesn't even need a stored map. Inertial navigation systems, or INS, which have been used in submarines, aircraft, and missiles since the mid-20th century, track the drone's movement purely from its own sensors. Remember the accelerometer and gyroscope from our earlier discussion? If you know your starting position, and you continuously measure every acceleration and rotation from that point forward, you can mathematically calculate your current position at any moment by integrating the acceleration data twice over time. First integration gives you velocity, second gives you displacement. Add the displacement to your starting position and you know where you are. The problem is drift. Those small errors in the gyroscope and accelerometer that we talked about, the ones that the Kalman filter compensates for using GPS? Without GPS corrections, those errors accumulate. A tiny bias in the accelerometer, just a tiny fraction of an inch per second squared, becomes yards of position error after minutes, and hundreds of yards after hours. Military-grade inertial navigation systems use extraordinarily precise sensors. Ring laser gyroscopes and fiber optic gyroscopes that can cost tens of thousands of dollars to minimize this drift. Consumer drones use much cheaper MEMS sensors that drift rapidly. But here's the key insight. You don't need to choose one system or the other. You can use all of them together, layering their strengths. GPS provides absolute position when available. Visual navigation provides position when GPS is jammed. Inertial navigation fills the gaps between visual fixes, maintaining position awareness during the seconds or minutes when neither GPS nor a clear visual reference is available. The Kalman filter, that same algorithm we met in the balance chapter, fuses all these sources together, weighting each one according to its current reliability, constantly adjusting, constantly predicting, constantly correcting. The result is a navigation system that is remarkably hard to defeat. To blind a drone equipped with this layered approach, you would need to simultaneously jam its GPS, jam its control link, block its view of the ground, and somehow degrade its inertial sensors, all at the same time. Lose any one layer, and the others compensate. The drone keeps flying, keeps navigating, keeps pursuing its mission. And there's one more dimension to this resilience that's worth mentioning. The same AI that enables visual navigation can also enable visual target recognition. A drone that can match ground features to a stored map can also match a target's visual profile to a stored image. Fly the drone to the general area of the target using inertial navigation. Then let the AI identify the specific target, a particular type of vehicle, a specific building, a distinctive structure, using its camera. The target becomes its own GPS coordinate, visible and identifiable without any external signal. This layered approach is what the quantum systems engineers described when they explained what happens when their drone flies into clouds. If there really is closed cloud cover, I don't have any navigation options at that moment. But because our autopilot has a gyro compass system, it can find its way for a limited time until there's a break in the cloud cover or we've flown lower to get below the clouds. And then I can use this solution to immediately find my way back to where I am in the world.
I emerge from the clouds and identify these 5 items on the ground. Check my maps to see where they are, and then I know where I am again. The loop, in other words, had become resilient. It no longer depended on any single source of information. Knock out GPS and it navigated visually. Block the video link and it navigated inertially. Each vulnerability spawned a backup system, and each backup system was folded into the same Kalman filter that was already combining the gyroscope and accelerometer data, making the fusion seamless and automatic. One engineer from Quantum Systems described the dynamic precisely. It's a constant game of cat and mouse. We see that for a while we can deal with these situations better. On the other hand, it's also clear that the opposing side is also constantly working on electronic warfare. There will never be a situation where one side has the constant upper hand. But we have to continuously react and improve the methods we can implement.
The arms race had moved inside the loop itself. And the next question it raised was this: if a drone can fly, balance, navigate, and see without any help from a human pilot or any external signal, what's left for the human to do? And equally urgent, how did all of this extraordinary technology become so cheap that volunteers could build it in their kitchens? To understand why a $400 drone can do things that a $30,000 drone couldn't do 15 years ago, you need to understand something about the economics of electronics manufacturing. And that story passes through one city more than any other: Shenzhen. Shenzhen in southern China, just north of Hong Kong, is not a city in the usual sense. It's more like a vast, humming factory floor that happens to also have apartments and restaurants and parks. It is the global epicenter of consumer electronics manufacturing, the place where your smartphone was probably assembled, where the components of your laptop were probably made, and where the parts of almost every consumer drone on the planet are produced. The key to Shenzhen's influence on the drone story is a concept called the component ecosystem. When you build a drone, you need motors, propellers, electronic speed controllers, flight controllers, GPS receivers, cameras, batteries, transmitters, receivers, and frames. Each of these components has to be designed, manufactured, tested, and delivered. In most places in the world, sourcing all these parts from different suppliers would be a logistical headache, requiring contracts with factories in different countries, long shipping times, and high costs for small orders. In Shenzhen, every one of these components is manufactured within a few hours' drive. The supply chain is dense, flexible, and fiercely competitive. If you need 1,000 brushless motors by next Tuesday, there are a dozen factories within driving distance that can deliver them. If you need a custom ESC With slightly different firmware, there's an engineer around the corner who can modify the design. And the prices, because of competition and scale, are extraordinarily low. This is the infrastructure that made DJI possible. When Wang Tao was developing the Phantom 1, he didn't have to design a brushless motor from scratch or build a GPS receiver. He could pick components off the shelf from suppliers who were already mass-producing them for smartphones and model airplanes and industrial automation systems, and integrate them into his flight controller. The Phantom 1's GPS came from U-Blocks, a Swiss company whose receivers were also in car navigation systems. Its processor came from ARM, a British chip design company whose architecture powered most of the world's phones. Its accelerometers came from Freescale's Semiconductor. Its compass from Honeywell. All widely available, all mass-produced, all cheap. And this is the crucial point. The components that make a drone fly are the same components that make a smartphone work. A gyroscope, an accelerometer, a GPS receiver, a processor, a camera, a radio transmitter. Your phone has all of these. The drone adds motors, propellers, and a battery large enough to fly. But the electronic heart of the machine is consumer electronics, riding the relentless downward curve of Moore's law and the global demand for billions of smartphones every year. When the smartphone industry drives the price of a MEMS gyroscope from $10 to 50 cents, drones get cheaper. When camera sensor manufacturers compete to put higher resolution sensors into thinner phones, drone cameras get better. When battery chemistry improves to give phones longer life, drones get longer flight times. The drone industry is a parasite on the smartphone industry, and the smartphone industry is enormous and cost-driven and constantly improving. The drones ride the wave for free. This is why the price dropped so dramatically. Wang Tao's $30,000 helicopter in 2008 used specialized components and hand-tuned firmware. The Phantom 1 in 2013 used mass-market components and standardized software, and it cost $1,000. By 2020, FPV racing drones using similar components could be built from kits for $300 to $400. And in Ukraine, soldiers and volunteers discovered that these same cheap racing drones, the same ones that hobbyists flew through obstacle courses for fun, could carry explosive charges weighing up to about 13 pounds when cable tied to the underside of the frame. The economics are staggering and worth sitting with for a moment. A Javelin anti-tank missile, one of the most effective infantry anti-armor weapons in the world, costs about $178,000 per unit. For the same amount of money, you can buy somewhere between 250 and 500 FPV drones, each carrying a warhead that can disable or destroy a vehicle. As one soldier fighting in Ukraine put it, "We don't want a Javelin. We'd rather take the FPVs, because one Javelin, I can get 250 to 500 FPVs, and at 250, they'll be the big ones with a thermal camera. Each one can carry a tank-destroying munition that we can make ourselves in a shed." Men in sheds. That phrase is worth pausing on. The soldier is describing a reality where the warheads that FPV drones carry are manufactured in workshops, garages, basements, not in defense contractor factories with billion-dollar budgets and decade-long development cycles, but in rooms with workbenches and soldering irons and bags of parts from AliExpress. Men in sheds are capable of making just as dangerous things as any defense company at the end of the day, the soldier said. And he wasn't exaggerating. Across Ukraine, in workshops run by non-profit organizations and volunteer groups, recovering veterans learn to build combat drones. If you like IKEA, making drones is like making IKEA, one volunteer organizer explained. Everyone is building drones in Ukraine, in the kitchen, just sitting and making a drone. The asymmetry this creates is one of the defining features of modern warfare. A consumer quadcopter that costs $400, assembled by a volunteer in a kitchen from commercially available parts, can destroy a main battle tank that costs several $million. A swarm of commercial drones, each cheaper than the ammunition used to shoot it down, can overwhelm air defenses designed to counter far more expensive and far fewer threats. The defenders find themselves in a terrible economic bind. Every drone they shoot down costs them more, often much more, than the drone itself cost the attacker. In workshops across Ukraine, and now also in the Netherlands and other allied countries, volunteers sit at workbenches assembling combat drones from commercial components. The process looks startlingly domestic. A person in a well-lit room, a soldering iron, a bag of parts, and an instruction video playing on a laptop. What we're doing here is just basic, what you can do at home with your son or with your daughter, one workshop organizer in the Netherlands explained. If you like IKEA, making drones is like making IKEA. The implications of that analogy are profound. When a weapon system can be assembled with the same skill level as flat-pack furniture, from parts available in any electronics market on Earth, the traditional model of arms manufacturing, with its classified designs, its controlled supply chains, its decade-long development cycles and billion-dollar budgets, is fundamentally disrupted. The barriers to entry have collapsed. The smallest military force, the poorest insurgency, the most determined volunteer group, can now field guided munitions. The monopoly on precision strike capability that advanced nations maintained for decades, based on the enormous cost and complexity of their weapon systems, is eroding. This is the economic paradox that the drone revolution has created. The feedback loop that keeps a drone in the air is made of the same commodity electronics that power a smartphone. The motors that spin the propellers are the same motors that power electric scooters. The cameras that give it sight are the same cameras in dash cams and baby monitors. The raw materials of this revolution are available to anyone, anywhere, for a few $100s. There's a geopolitical dimension to this that's worth noting, without lingering on the politics. China, and specifically Shenzhen, is by far the world's largest producer of drone components. Motors, propellers, ESCs, batteries, frame materials, camera sensors, GPS modules, flight controllers, all are manufactured predominantly in China. DJI itself, the company that created the consumer drone market, is a Chinese company headquartered in Shenzhen. A soldier fighting in Ukraine described the dependency bluntly. China makes all our electronic components. I use electronic components to make circuit boards, to make timers for the bombs we use all the time. Can I find components that are made outside of China? No. This dependency creates a fundamental strategic vulnerability. If the supply of Chinese components were disrupted, whether by sanctions, by conflict, or by China's own strategic decisions, the ability to build drones at current prices and volumes would be severely compromised. It would be, as one defense analyst put it, like discovering that all the ammunition for your weapons is manufactured by a potential adversary, and no amount of export controls or trade restrictions can easily put this genie back in the bottle. Because the genie is a consumer electronics supply chain that serves billions of customers and whose products are in every pocket on the planet. You cannot restrict the sale of brushless motors without affecting every electric scooter, every washing machine, every industrial robot that uses them. You cannot restrict MEMS sensors without affecting every smartphone. The dual-use nature of these components, the fact that they are simultaneously toys and weapons, is the fundamental challenge. So, if a single drone is this cheap and this effective,
What happens when you have not one but 100 of them, flying together, communicating with each other, organizing themselves without any human directing each one individually? What happens when the loop multiplies? In 2016, at the China Lake Weapons Testing Station in the California desert, something happened that the Pentagon's Dr. Will Roper described as a glimpse into the future of combat. From 3 F-18 fighter jets traveling at nearly the speed of sound, 103 tiny drones were ejected into the atmosphere. Each drone was called Perdix.
It was about the size of a human hand, weighed roughly 10 ounces, and had been designed and built by 20 and 30-somethings from MIT's Lincoln Labs. It was cheap enough to lose. It was printed on a 3-dimensional printer, and it was designed not to survive, but to be expendable. A tool for one mission, replaced by the next batch off the printer. Roper himself described his first reaction to seeing it. I held it up in my hands, about as big as my hand, and I looked at it and said, "Really? This is what you want me to get excited about? It looks like a toy." But Perdix was not a toy, because the 103 drones that were ejected from those fighter jets were not individually controlled by any human. They were given a mission, a collective task. Patrol a 3-square-mile area. And then they were left to figure out how to do it on their own. Think about what that requires.
100 small aircraft, all in the same airspace, each one capable of independent flight, need to divide the area among themselves, establish positions, avoid colliding with each other, adjust their formation if one of them malfunctions, and maintain coverage of the entire zone, all without any human directing each individual drone. The pilots on the ground set the objective. The drones collectively determined the strategy. "We've given them a mission at this point," Roper explained, watching on a computer screen. "And that mission is, as a team, go fly down the road, and so they allocate that amongst all the individual Perdix, and they're talking to each other." And they were talking a lot. "How frequently are they talking back and forth to each other?" a reporter asked. Many times a second when they're first sorting out," Roper said. "It looks helter-skelter. You want them to converge to a good enough solution and go ahead and get on with it."
It's faster than a human would sort it out. This is swarm intelligence, and it's a fundamentally different paradigm from traditional drone control. In a conventional setup, one pilot controls one drone. The pilot is the brain, the drone is the body. The feedback loop runs through the human. The drone sends video, the human sees it. The human sends commands, the drone executes. One brain, one body. In a swarm, there is no single brain. Each drone has its own small computer running its own algorithms. But each drone also communicates constantly with its neighbors, sharing its position, its status, its plans. Collectively, through this chatter, the swarm organizes itself. No drone is in charge, no human is directing individual units. The behavior of the swarm emerges from the interactions of its members, the same way a flock of starlings creates those breathtaking, shifting patterns in the sky, without any bird being the leader. The feedback loop is no longer between one sensor and one motor. It is between many drones, many sensors, many motors, all linked together in a network where information flows in every direction, and decisions emerge from the collective. Each drone is running its own internal loop, balancing, navigating, avoiding obstacles. But on top of that internal loop, there's a social loop, a conversation with the swarm that coordinates the behavior of the whole. In 2021, A swarm in a Pentagon test overcame an even greater challenge. The drones completed an obstacle course, navigating between buildings and high-voltage power lines. They worked together with unmanned ground vehicles. Over 100 drones controlled by a single human operator. One person, 100 aircraft. That ratio, that leverage, is what makes swarms so significant. In a world where each drone requires a dedicated pilot, the limiting factor is the number of trained pilots. In a world where one person can command a swarm, the limiting factor is the number of drones you can build, which, as we just discussed, is essentially limited only by your budget and your access to consumer electronics. Chinese researchers have pushed the concept further still. In a widely circulated video, a swarm of drones navigated autonomously through a dense bamboo forest, each drone using its own cameras and ultra-wideband sensors to detect individual branches and adjust its path in real time. The drones maneuvered independently around obstacles, but the swarm stayed together, maintaining formation while flowing through the forest like water flowing through a grate. Each drone was making hundreds of decisions per second about its own path, while simultaneously coordinating with its neighbors to maintain the collective structure. Perdix can be used as decoys to confuse enemy air defenses or equipped with electronic transmitters to jam their radar. Fitted with cell phone cameras, a swarm of Perdix could hunt down fleeing targets by searching multiple roads simultaneously. There are several different roads they could have gone down, and you don't know which one to search, Roper explained. You can tell them, go search all the roads, and tell them what to search for, and let them sort out the best way to do it. The drones divide the work among themselves, without any human assigning each drone to a specific road. The swarm decides. The test that day was not only a technological milestone, it was a public one. Roper had agreed to let cameras record the outcome, a risky decision. My first response was, "That sounds like a horrible idea," he admitted. "I don't want this to fail on camera." But I did not like the fear of failure being my only reason for not letting you be here. And we also wanted the world to see that we're doing some new things. The F-18s released the Perdix at nearly the speed of sound. The tiny drones survived their violent ejection into the atmosphere, organized themselves into a swarm, and completed their mission. 104 in the swarm, alive and coordinating. In 2021, an even more ambitious test had the drones navigate through an obstacle course, finding their way between buildings and high-voltage power lines without accidents, and coordinating with unmanned ground vehicles. A single person controlled the entire swarm. One operator over 100 aircraft. Now, think about what that ratio means in military terms. The traditional model, one trained pilot per aircraft, means your air power is limited by the number of pilots you can recruit, train, and sustain. That takes years and costs millions per pilot. But if one person can command 100 autonomous drones, the bottleneck shifts entirely. You no longer need more pilots. You need more drones. And drones, as we've established, are cheap and getting cheaper. The military implications are, frankly, unsettling to contemplate. A security expert described one scenario. You can imagine that a swarm of drones can fly waves of attacks. You attack once, you've made a hole in a bunker, then the next drones come and fly in and blow up the next hole. Another possibility. Flying minefields. You fly the drones in an area and say it's now off limits. Nothing is allowed to fly in or run in and will shoot down anything that does so.
a temporary minefield in the air. And the fundamental challenge for anyone trying to defend against a swarm is that the economics we just discussed apply at scale. If one drone costs $400, 100 drones cost $40,000. That's still less than a single anti-aircraft missile. The defender needs to shoot down every drone in the swarm. The attacker just needs a few to get through. Mass overwhelms defense. Quantity has a quality all its own. There are already plans for a drone wall, a continuous surveillance barrier extending along NATO's eastern flank from Norway to Poland, using autonomous drones to patrol border sections, sharing imagery and intelligence among themselves, watching and waiting. The machines would monitor, report, and potentially respond, without human crews exposed to danger. The concept is still in its early stages, but as one security analyst observed, it shows the direction things are heading. Monitoring borders with drones is being done more and more, and it makes a lot of sense to take advantage of drones' endurance and reduced vulnerability to make regular patrol flights. The vision extends beyond border patrols. Defense planners envision what they call the combat cloud, a networked system connecting manned and unmanned platforms across all domains, air, land, and sea, sharing sensor data in real time and coordinating actions across hundreds or thousands of platforms simultaneously.
Manned fighter jets would fly alongside autonomous wingmen, unmanned combat aircraft that navigate independently and carry out risky missions on behalf of the human pilot. For the pilot, it's ultimately almost irrelevant whether the receiver is a manned or unmanned aircraft, one test pilot explained. We're simply replacing the pilot of the wingman aircraft. Critical decisions, such as the order to shoot, would remain with the human in the cockpit. But the wingman would handle its own flying, its own maneuvering, its own sensor operation, all through the same feedback loops we've been discussing, just scaled up to the size of a fighter jet. The largest drone being developed in Europe, the Euro drone, has a wingspan of about 92 feet, 2 engines, a flight time of over 40 hours, and a payload capacity of more than 4,000 pounds. It is designed to fire guided missiles, drop rescue platforms, and provide continuous surveillance from a distance of about 12 miles. With a price tag in the billions, it is at the opposite end of the cost spectrum from the FPV drones built in kitchens. And yet, both machines run on the same fundamental principle: sense, compute, correct. The loop scales. And the revolution isn't limited to the air. The same principles of feedback, autonomy, and asymmetric cost are spreading to sea and land. Ukraine's home-built surface drones, remote-controlled boats packed with explosives and costing less than about $200,000 each, have devastated Russia's Black Sea fleet, damaging or destroying warships worth tens of millions of dollars. The maneuverable boats attack in groups, their operators piloting them via satellite link from hundreds of miles away. Underwater, the Manta Ray, an American unmanned submarine prototype, glides through the sea like a giant ray, designed to carry out missions at extreme depths with almost infinite range. Anduril's Dive XL, an autonomous submarine about the size of a school bus, can travel 1,000 miles fully submerged, following pre-programmed mission objectives without communicating with its controllers. If I told you to go off and perform some mission months long, Lucky explained, like, go to this target, listen for this particular signature, and if you see this signature, run. If you see this one, hide. If you see this one, follow it. It can do that all on its own without being detected, without communicating with it. On the ground, robotic vehicles powered by AI are learning to navigate terrain autonomously, carrying ammunition, evacuating wounded, and conducting patrols. Some can follow a human soldier autonomously, recognizing the person through their camera and AI, walking behind them like a mechanical pack animal, leaving the soldier's hands free for their weapon and their attention free for their mission. So, what happens on the other side?
If the drone and the swarm represent the spear, what does the shield look like? How do you fight a machine that can see in the dark, navigate without GPS, fly in swarms of hundreds, and costs less than a decent bicycle? The problem of shooting down a drone is, in principle, simple. It's a physical object in the air, and if you can detect it and hit it, it will crash. But in practice, each step of that process, detect, track, identify, engage, is harder than it sounds, and the reasons are instructive. The military framework for engaging a drone follows the same find, fix, track, engage sequence as any other target. But each step presents unique challenges that make counter-drone operations far harder than they might initially seem. Start with detection. Traditional military radar systems, the kind that have defended airspace since the Cold War, were designed to find large, fast objects at high altitude. Aircraft, missiles, bombers.
They scan the sky in broad sweeps, looking for strong radar returns from objects with large metal surfaces. A quadcopter drone, by contrast, is small, often made largely of plastic, flies low to the ground, and moves relatively slowly. To a radar designed to track fighter jets, a small drone can be almost invisible, lost in the clutter of ground reflections and background noise. This is exactly the problem that was exposed in one of the most alarming security incidents in recent American military history. In December 2023, over 17 consecutive nights, swarms of unidentified drones flew over Langley Air Force Base in Virginia, home to dozens of F-22 Raptors, the most advanced stealth fighters ever built. An eyewitness on the nearby James River described what he saw. They started really coming in, almost like on a conveyor belt. I probably saw upwards of 40 plus. They were going directly over Langley Air Force Base. A retired four-star general who was the highest-ranking officer at Langley to witness the swarm went to the roof for an unobstructed view. What you saw was different sizes of incursions of aircraft, he recalled. The smallest, you're talking about a commercial-size quadcopter, and the largest ones are probably the size of a small car. The size of a small car. Flying over one of the most critical air bases on the East Coast, and nobody could stop them. As the head of NORAD acknowledged, NORAD's radar systems, designed during the Cold War to detect high-altitude airspace or missile attacks, were unable to detect low-flying drones that could be seen with the naked eye. Fighter jets were scrambled. Airborne warning and control aircraft were deployed. None of it was effective. Some of the F-22 Raptors, among the most expensive aircraft in the world, were moved to a different base for their own protection. After 17 nights, the drone visitations simply stopped. No one was caught. No one was identified. The investigation remains, as of the time of this recording, unresolved. The incident laid bare a gap in the most powerful military on Earth's defensive capabilities. Drones could fly over a major American airbase repeatedly for weeks, and the military could not stop them or even reliably track them. So, new radar systems are needed. Systems designed specifically to detect small, low-flying, slow-moving targets. These exist, but they require different frequencies, different antenna designs, different signal processing, and they tend to produce many more false alarms, because a small drone's radar signature can be similar to a bird, a plastic bag in the wind, or even a weather disturbance. Radio frequency detection offers another approach. Since most drones communicate with their operators via radio, you can scan the electromagnetic spectrum for the characteristic signals of drone control links and video transmitters. If you detect a drone's radio emission, you know one is nearby, and you can often estimate its direction and distance. But this method fails for drones that don't emit radio signals. Autonomous drones following pre-programmed waypoints, fiber optic drones, or GPS-guided, kamikaze drones on a one-way mission with no need for a control link. Acoustic detection, listening for the distinctive sound of spinning propellers, works at short range, but is easily overwhelmed by wind, traffic, and battlefield noise. The reality is that detecting a small drone reliably, especially in a cluttered environment like a city or a forest, remains a significant challenge. And if you can't detect it, you can't shoot it down. Now assume you've detected a drone. You've tracked it, identified it as hostile rather than one of your own. How do you bring it down? The first option is jamming, which we've already discussed.
If you can identify the frequencies the drone uses for its control link and GPS, you can try to drown them out. This works well against simple drones with no autonomous capability, the kind that just fall out of GPS mode and drift when jammed, or trigger a return to home failsafe. But as we saw in the previous chapter, the newest drones are increasingly jam-resistant. They navigate visually, they use fiber optic links, they have inertial backups. Jamming is an arms race, and the drones are gaining ground. Kinetic solutions, meaning you physically hit the drone with something, come in several flavors. Traditional anti-aircraft guns can be adapted for drone defense, but they were designed for much larger, faster targets and tend to use expensive ammunition. Germany's Rheinmetall, one of Europe's largest defense contractors, has developed a system called Sky Ranger, specifically designed for counter-drone operations. It uses radar and other sensors to detect and track drones, algorithms to classify targets as threats, and a cannon that fires 1,250 rounds per minute of airburst ammunition, shells that detonate near the drone and spray it with fragments, knocking it out of the sky. But there's that economics problem again. Each round of airburst ammunition costs money. Each drone costs $400. If you're firing expensive specialized ammunition at cheap drones, you're losing the economic exchange, spending more on defense than the attacker spent on offense. This is why directed energy weapons, lasers and high-power microwaves are receiving so much attention and investment. A laser weapon generates a focused beam of light that can burn through a drone's structure, overheat its electronics, or blind its camera. The cost per shot is, in principle, remarkably low, essentially just the cost of the electricity to power the laser, perhaps a few dollars per engagement. The beam travels at the speed of light, so there's no need to lead the target as you would with a bullet. And the magazine is effectively unlimited. As long as you have electricity, you can keep firing. High-power microwave weapons take a different approach. Instead of a focused beam that burns a single point, they emit a broad pulse of electromagnetic energy that can disrupt or destroy the electronic circuits inside a drone over a wide area. In theory, a single microwave pulse could disable multiple drones in a swarm simultaneously, without needing to aim precisely at each one. But both technologies have limitations. Lasers require a clear line of sight and are degraded by rain, fog, and smoke, exactly the kinds of conditions that are common on a battlefield. They also take time to burn through a target, typically several seconds of sustained focus, during which the drone is still flying and potentially maneuvering.
High-power microwaves can affect friendly electronics as well as hostile ones, and their effective range and reliability against hardened targets are still being refined. Drone-on-drone interception is another growing approach. A defender launches its own drone, a fast, agile interceptor, and flies it directly into the attacking drone, destroying both on impact. This is kinetic kill at its simplest. Crash into the enemy. Anduril, the California defense company founded by Palmer Luckey, builds a system called Roadrunner, a twin turbojet-powered drone interceptor that can take off autonomously, identify and strike an incoming drone, and, If it doesn't find a target, land and try again later. The economics are better than missiles. Each interceptor is cheaper than a traditional anti-aircraft missile, but still more expensive than the cheapest attacking drones.
One of the most creative, and in some ways most sobering, defensive approaches observed in the Ukraine conflict involves something decidedly un-high-tech: physical barriers. Troops have constructed sarcophagi, protective enclosures of concrete and metal mesh, around critical infrastructure like oil refineries and electrical transformers. Metal netting stretched between poles, like giant volleyball nets, can snag or deflect drones that fly into them. In Ukraine's Sumy region, defenders have wrapped electrical transformers and substations in stone sarcophagi, heavy protective enclosures that absorb the blast and fragmentation from incoming drones. Attacking forces reported that it took days of sustained drone attacks to methodically break through these enclosures and reach the protected equipment underneath.
And in the war at sea, crews on vulnerable cargo ships and tankers have discussed wrapping their bridge structures, the control centers that drone operators typically target, in metal netting to catch or deflect incoming FPV drones. These are strikingly low-tech solutions to a high-tech problem, and their effectiveness varies. But they illustrate a fundamental point that recurs throughout the history of military technology. Sometimes, the best counter to a sophisticated electronic system is a physical obstacle that requires no electricity, no software, and no maintenance. A concrete wall doesn't care whether the drone navigating toward it uses GPS, visual navigation, or fiber optic control. It's just a wall. And the drone hits it instead of the thing behind it. There's an even more creative defensive concept that emerged from the war in Ukraine: drone-on-drone interception. Rather than using expensive missiles or specialized cannon systems, you send up your own small, fast interceptor drone to crash directly into the attacking drone. It's kinetic kill at its most basic. Fly into the enemy and destroy both drones on impact. Both Russian and Ukrainian forces have developed interceptor drones with auto-targeting systems that can lock onto an incoming drone and pursue it. And by some accounts, Russian forces achieved an early lead in this specific technology. The economics are better than missiles, since each interceptor can be built cheaply from the same consumer components as the attacking drone. But the challenge is reaction time and detection. You need to spot the incoming drone early enough to launch and position your interceptor. Anduril, the California defense company founded by the young billionaire Palmer Luckey, has built an interceptor called Roadrunner, a twin turbojet-powered drone that can take off on its own, scan for incoming threats, and strike them autonomously. If it doesn't find a target, Luckey explains, it can land and try again. The machine is reusable, at least until it actually intercepts something, at which point both machines are destroyed. And Anduril's electromagnetic warfare system can be programmed to jam specific frequencies, knocking out entire drone swarms electronically before they reach their target. The overall picture is sobering for defenders. There is no single silver bullet against drones. Effective drone defense requires layering. Multiple detection systems covering different sensor modalities, multiple engagement options covering different ranges and drone types, electronic warfare to jam and spoof, kinetic systems to shoot down what gets through the jamming, interceptor drones to chase what the kinetic systems miss, and physical barriers to protect the most critical targets. Each layer adds cost. Each layer requires maintenance, training, and integration with the other layers. And each layer must be updated constantly, because the drones it was designed to defeat last month may already have been replaced by a new variant that exploits a weakness the defenders hadn't anticipated. The total cost of a comprehensive counter-drone system for a single military base or critical infrastructure site can run into the tens of millions of dollars. The total cost of the attacking drone swarm it's designed to defeat might be a few $100,000.
The economic asymmetry runs in the attacker's favor at every level, from the individual engagement to the strategic balance sheet. And this asymmetry is getting worse, not better, as drone technology continues to ride the cost curve of consumer electronics downward, while defense systems remain bespoke, specialized, and expensive. This is the defender's dilemma, and no one has solved it. Every military planner working on counter-drone strategy is wrestling with the same fundamental question. How do you defend against a threat that costs less than the ammunition you use to shoot it down? And how do you do it at scale, when the attacker can field thousands of drones for the price of a single fighter jet? It is expensive, complex, and, crucially, it is slower to evolve than the drones themselves. The reason for this asymmetry in adaptation speed is worth understanding. A defense system like Skyranger or a laser weapon is a large, complex, expensive platform developed by major defense contractors over years of engineering and testing. A new attacking drone can be designed, prototyped, tested in the field, and deployed in weeks. The front line in Ukraine functions as a live laboratory, where new drone designs are tested in combat. Feedback is received within hours, modifications are made, and updated versions are sent back to the front. As one quantum systems engineer described it, the battlefield fuels development. It's a new kind of race because drones, the key technology of the future, are not developed over the course of years, but are instead updated in a matter of days. Days. Think about that in comparison. A major defense system like the Eurodrone, a large European reconnaissance platform with a 92-foot wingspan, has been in development by a consortium of 4 countries for years and is not expected to enter service until 2030 or later. A new type of FPV attack drone can go from concept to combat deployment in weeks. The defense industry operates on government procurement timelines, with requirements documents, competitive bidding, contract negotiations, developmental testing, and production ramp-up, each stage taking months or years. The drone innovators operate on startup timelines, or sometimes on no formal timeline at all, just a soldier with a problem and a workshop with parts. Quantum Systems, the Bavarian drone company, has a branch office in Ukraine, building, repairing, and developing drones close to the front line, receiving feedback from drone units almost daily, and implementing solutions in near real time. The battlefield fuels the development.
The loop of build, test, learn, adapt runs faster than any peacetime procurement process could match. That gap in iteration speed is, in some ways, the most important fact about the entire drone revolution. The attackers can innovate faster than the defenders can respond. And until the defense industry finds a way to match that speed, the advantage will continue to shift toward the drones. And now we arrive at the question that looms over all of this. The question that makes engineers uncomfortable and ethicists lose sleep and diplomats scramble for language that everyone can agree on. Because everything we've talked about, every layer of the feedback loop, has been leading here, and the trajectory is unmistakable. The loop has learned to balance. It has learned to navigate. It has learned to see. It has learned to resist jamming and navigate without GPS. It has learned to coordinate with other loops in a swarm. And at each stage, the role of the human in the loop has gotten smaller. The pilot used to control every movement. Then the pilot gave waypoints, and the drone flew itself between them. Then the pilot designated a target, and the drone tracked it autonomously. Then the pilot supervised a swarm. What happens when the pilot is removed entirely? What happens when the loop decides? Let's be precise about what we mean by an autonomous weapon, because the term gets thrown around loosely and it helps to be specific. In military terminology, there's a framework called the kill chain.
It's the sequence of steps between identifying a potential target and engaging it. The steps are usually described as find, fix, track, engage, and assess. Find means detecting something that might be a target. Fix means confirming its identity and location precisely enough to attack. Track means keeping watch on it as it moves. Engage means carrying out the attack. Assess means evaluating the results. In a traditional setup, a human is involved at every step. A human analyst finds the target on a reconnaissance feed. A human intelligence officer confirms its identity. A human commander authorizes the strike. A human pilot or operator pulls the trigger. A human observer assesses the damage. The loop passes through human judgment at every stage. Now, think about what happens as each of these steps gets automated. AI-powered image recognition can find and fix targets far faster than a human analyst can scan a video feed. The AI is trained to distinguish between types of vehicles, between soldiers in different uniforms, between military and civilian objects. At Quantum Systems, the Receptor AI system can identify and classify targets autonomously, freeing the drone operator from having to manually scan every yard of terrain. As their managing director explained, the AI is trained to distinguish between soldiers and vehicles based on uniforms and vehicle types. The drone can pursue its target autonomously without the drone operator having to control it. Tracking is, in many ways, the easiest step to automate. Once a target is identified, keeping a camera pointed at it as it moves is a well-solved computer vision problem. Commercial drones have had "follow me" modes for years, tracking a moving subject automatically. The same algorithms that let a consumer drone track a jogger through a park can track a vehicle through a city. The same software that lets a photography drone keep a moving subject centered in the frame can keep a weapon locked on a target as it maneuvers. The dual-use nature of the technology, that theme we keep returning to, is nowhere more apparent than here. Engagement, the actual strike, is already partially automated in many systems. Guided munitions that lock onto a laser designator, missiles that home in on radar emissions, torpedoes that follow acoustic signatures. These are all weapons that, once launched, find and strike their target without further human guidance. The step from a missile that guides itself to a drone that guides itself is, technically, a short one. Assessment. Evaluating the outcome of a strike can also be performed by AI, comparing before and after imagery to determine whether the target was destroyed. That leaves engage, the moment of action. The decision to fire, to detonate, to kill. And here is where the conversation becomes genuinely difficult. Technically, the entire kill chain can be automated. As one researcher put it, you can do all of these steps with algorithmic systems. In principle, they exist. The software exists. The hardware exists. A drone with a camera, AI recognition software, a navigation system, and an explosive payload could, today, find a target, confirm its type, track its movement, fly into it, and detonate, all without any human involvement after the initial programming. Whether it should is a different question entirely. A Pentagon directive states that autonomous weapon systems shall be designed to allow commanders and operators to exercise appropriate levels of human judgment over the use of force. The Vice Chairman of the Joint Chiefs of Staff, General Paul Selva, was asked directly about this. A reporter noted that machines are now better at facial recognition than humans. So if the machine's better, why not let it make the decision? The reporter asked. General Selva's answer was careful. This goes to the ethics of the question of whether or not you'll allow a machine to take a human life without the intervention of a human. And when the reporter pressed, "Do you know where this is headed?"
The general replied, simply, "I don't." That uncertainty is shared across the field. The United Nations has been working for years on an international agreement to regulate autonomous weapons systems, with a deadline of late 2026. In Geneva, an international working group is drafting a document that must be acceptable to all member states, including China, the United States, and Russia. The negotiations are, by all accounts, extraordinarily difficult. There is no consensus on even basic definitions. What counts as autonomous? Where in the kill chain must a human be involved? Is a human who merely switches a system on and lets it operate considered to be in the loop? How do you verify compliance, and what are the consequences for violations? We still have a chance to put those rules in place before the weapons are deployed, one diplomat involved in the negotiations said. We also need to discuss the points at which humans must be involved. Simply saying they need to be is not enough. The challenge of making these talks meaningful is that all the major powers must agree, including nations whose militaries are actively developing autonomous systems, and whose strategic interests may be served by deploying them as quickly as possible. And all the while, the technology keeps advancing, indifferent to the pace of diplomacy. And all the while, the technology keeps advancing, indifferent to the pace of diplomacy. One Russian military analyst, describing the current trajectory of drone warfare, laid it out with striking clarity. The era of FPV is ending. Each FPV needs a pilot, and pilots can be targeted. The future is autonomy. To build vision-based autonomous targeting, you need processors at least as powerful as the ones in a smartphone. And that is something Russia cannot manufacture domestically. The analyst identified this as a critical dependency. The ability to build autonomous drones requires access to advanced semiconductor chips, and the global supply of advanced chips is controlled by a handful of companies, none of them Russian. We are fully dependent on China in this regard, he acknowledged, and if we cannot break through on domestic electronics manufacturing, we will not catch up. The same dynamic applies in reverse. Western nations, which design the most advanced chips, depend on Asian manufacturers to produce them, and everyone, East and West, depends on the same Shenzhen supply chain for the motors, batteries, and components that go into the drones themselves. The global web of dependencies is so tangled that no single nation can fully control the technology, and no single embargo can fully prevent its spread. Think about what that means in practical terms. The processors that enable autonomous targeting in military drones are fundamentally the same processors that enable facial recognition in your phone's camera app. The same ones that run the autocomplete on your keyboard. The same ones that power the recommendation algorithm in your music streaming service. The AI that can identify a tank in a thermal image is trained using the same machine learning frameworks that identify your friend's face in a photograph. The line between civilian artificial intelligence and military artificial intelligence is not a wall. It is a dotted line. And it is getting harder to see every year. But while diplomats negotiate and ethicists debate, the technology continues to advance, driven not by malice, but by the same engineering logic that has driven every layer of the feedback loop we've been following. Each improvement makes the drone more capable. Each capability makes the human less essential. And each step closer to full autonomy is driven by a specific, practical problem, usually the problem of electronic warfare. Think about it from the engineer's perspective. Jamming severs the link between pilot and drone. The obvious solution. Make the drone capable of completing its mission without the pilot. GPS spoofing sends the drone to the wrong location. The obvious solution: give the drone AI vision so it can recognize the target itself. Radio direction finding locates the pilot. The obvious solution: remove the radio link entirely. Make the drone autonomous so there's nothing to find. Every defensive measure against drones pushes drone developers toward greater autonomy, because autonomy is the ultimate counter to electronic warfare. You can't jam a decision that happens on board. AI decision support systems, algorithms that analyze data from multiple sensors and recommend targets to human operators, are already in use.
The step from recommending to deciding is technically a small one. It requires removing a single human approval step from the process, and the pressure to remove it comes from a very practical place: speed. In a world where a swarm of 100 drones is bearing down on your position, you don't have minutes to deliberate. You might not have seconds. The drones are moving at 60 miles per hour, each one capable of independent action, and the window to engage each one might be a fraction of a second. A human commander reviewing each engagement individually cannot keep pace. The system that can react fastest wins. This is the deep tension at the heart of the drone revolution, and it's worth sitting with. The feedback loop that we've been tracing through this story, from the simple sensor-motor correction that keeps a drone level to the complex AI that identifies and tracks a target, has been getting faster and smarter at every step.
Each improvement makes the drone more capable, more resilient, more effective. And each improvement also makes the human in the loop less essential. Not because the human's judgment is unimportant, but because the speed of the engagement is outrunning the speed of human thought. A drone operator in Ukraine described a moment that captures this tension with painful clarity. He was flying an observation drone with a camera, watching a Russian soldier on the ground. The soldier was alone, in a canoe, apparently drunk. The operator had the ability to drop a munition on him, and he chose not to. He was just an alcoholic who kept sneaking off to get drunk in a boat, the operator said. I decided that day to be Caesar and let him live. He dropped the bomb on a bunker full of soldiers a mile away instead. That was a human decision. A decision that took into account context, judgment, mercy. A machine, running through its algorithm, its find, fix, track, engage loop, would have classified the soldier as a valid military target. Uniform, weapon, on the battlefield, and engaged. The algorithm doesn't have a category for drunk in a canoe and not a threat. I think some of my friends killed him about a week later, the operator added. He was just an alcoholic who kept sneaking off to get drunk in a boat, and they weren't feeling as merciful as me. He was a soldier in uniform, with a gun, on the battlefield. One less person to worry about. When asked whether people are right to fear autonomous weapons, the same operator gave an answer that cuts to the heart of the matter. I think people always imagine, if they're up against a human, that there's always an element of mercy and compassion that might come in there. That the bad guy might have a moment of humanity and decide to spare you. With a robot, you're never going to get that. One researcher who studies the regulation of autonomous weapons described the dynamic with precision. The allure is that an AI system can identify potential targets very, very fast and at large scales. So then it becomes a production of targets, a production line of targets. But the idea is to not run out of targets, and that really subverts the idea of discriminatory warfare. If the mandate is all of a sudden to not run out of targets. The language itself, production line of targets, reveals how the logic of automation can reshape the logic of war. When finding targets is hard, slow, expensive, there's a natural constraint on the pace of killing. When it becomes easy, fast, and automated, that constraint evaporates. Palmer Luckey, the founder of Anduril, argues the opposite case with equal conviction. There's no moral high ground in making a landmine that can't tell the difference between a school bus full of children and Russian armor, he says.
It's not a question between smart weapons and no weapons. It's a question between smart weapons and dumb weapons. All Anduril weapons, he says, have a kill switch that allows a human to intervene if needed. The Secretary-General of the United Nations has called lethal autonomous weapons politically unacceptable and morally repugnant. Luckey's response is characteristically direct. Would you like it if NATO just had a bunch of guys sitting at typewriters? 1,000 monkeys writing letters to Vladimir Putin, begging him to not invade Ukraine? Our entire society exists because of a credible backstop of violence threatened by the United States and our allies all over the world.
Whether autonomous weapons save more lives than they take, whether they are more precise or more reckless, whether they make war more humane by removing human soldiers from danger, or less humane by removing human judgment from the decision to kill. These are questions that do not have easy answers. And they are questions that the technology is forcing us to confront, whether we're ready or not. What we can say is this: the loop is getting faster, smarter, and more independent. And the humans in it are making fewer and fewer of the decisions. Where that trajectory ends up is one of the most important questions of this century. And it is a question that is being shaped right now, today, on battlefields and in laboratories, and in conference rooms in Geneva, by people who are trying very hard to get the answer right, knowing that the consequences of getting it wrong are enormous. So, here we are. We started with a blade spinning in the air and a force pushing upward. We built a motor that could change its speed 1,000 times per second. We added sensors that could detect a 2-degree tilt before a human could blink, and a mathematical filter to make their imperfect readings precise, and a controller to turn those readings into corrections, and the loop was born. Sense, compute, correct. 1,000 times per second. We gave the loop a sense of place, GPS coordinates from satellites 12,000 miles overhead, and a compass and a barometer. And the drone that could only balance could now navigate, hold its position in the wind, fly waypoints, and come home on its own. We gave it eyes, cameras that could see down and forward and in the infrared, and what had been a flying instrument became a flying observer, seeing the world from above with a clarity and persistence that changed the meaning of the word battlefield.
We watched the loop break when the signals it depended on were jammed and spoofed. And we watched it fight back, teaching itself to navigate by looking at the ground, comparing what it saw with what it knew, closing the loop on its own sensors when the world outside went silent. We saw the loop get cheap, riding the tidal wave of consumer electronics that put a gyroscope and a GPS and a camera in every pocket, and we saw the consequences. $400 machines built in kitchens, changing the calculus of war. We saw the loop multiply, 100 drones organizing themselves in the air without human direction, dividing tasks, sharing information, flowing through obstacles like a flock of birds. We saw the defenders struggling to keep up, building radars and jammers and cannons and lasers and interceptor drones and physical barriers, layering defense upon defense, each answer arriving slower than the next question, each countermeasure more expensive than the threat it was designed to stop. And we arrived at the hardest question of all. What happens when the loop runs so fast and so well that there's no room left for a human to make a decision? Where does judgment live in a world of millisecond engagements? There's no tidy answer to that question tonight. And maybe that's okay. Maybe the value of sitting with it, turning it over slowly in the quiet of the evening, is that it stays with you. That the next time you hear the buzz of a quadcopter in a park, or see a drone shot on a nature documentary, or hear about a drone strike in the news, you'll think about the loop. The invisible, relentless, beautiful, troubling loop that makes it all possible.
And here's one last thing that might be worth holding gently as you settle deeper into your pillow. Your body is a feedback loop too. Right now, your vestibular system, a tiny structure in your inner ear that works on essentially the same principles as a MEMS gyroscope, is telling your brain which way is up. Your proprioceptors, sensors in your muscles and joints, are reporting the position of your limbs. Your brain is integrating all of this information, running its own version of a Kalman filter, fusing imperfect data from multiple sensors into a coherent picture of where you are in space, making thousands of tiny corrections per second to the muscles that keep you balanced and oriented. When you were a toddler, that loop was raw and untuned. You wobbled, you fell, you crashed. Just like an early drone with poorly tuned PID gains. But the loop learned. It got faster, smoother, more precise. Until now, decades later, you don't even notice it. You stand on one foot while putting on a sock. You catch yourself on a staircase before you consciously realize you've stumbled. The loop runs beneath your awareness, quiet and competent, 1,000 corrections per second, keeping you upright and balanced in a world that is constantly, gently trying to push you over. And tonight, as you lie there, that loop is finally allowed to slow down. The muscles relax. The corrections become fewer, gentler. The brain stops fighting gravity and surrenders to it. The frantic cycle of sense, compute, correct eases to a murmur, then a whisper, then something close to silence. This is what sleep is, in a way, the loop at rest. The system that spent all day keeping you balanced, oriented, aware, finally letting go. So let it let go. Let the sensors quiet down. Let the corrections stop. Let your own beautiful, ancient, improbable feedback loop, the one that has been keeping you upright and alive for every waking moment of your existence, take the rest it has earned. The drones will keep flying tonight. Somewhere over a dark field, a feedback loop is running, sensing and correcting and sensing again, 1,000 times a second. Somewhere in a factory in Shenzhen, a brushless motor is being tested for the first time, spinning up in the dark, its magnets pulling the rotor around in a frictionless whirl. Somewhere in a university lab, a graduate student is staring at the same equations that Wang Tao stared at 20 years ago, trying to make the Kalman filter converge just a little bit faster. Somewhere in a workshop, someone is soldering an ESC to a flight controller, building something that will fly tomorrow. And somewhere in a conference room in Geneva, diplomats are trying to write rules for a technology that is evolving faster than rules can be written, trying to draw a line around the loop, trying to decide where the human must stay inside it. All of it, every bit of it, traces back to that same simple idea. Measure, compute, correct, repeat. A blade spinning in the air, a chip
reading a gyroscope, a motor adjusting its speed by a fraction of a percent. 1,000 times a second. That's all it is. And it has changed the world. But you don't need to change anything tonight. You don't need to balance or navigate or see. The corrections can wait. The loops can wait. Everything is taken care of by systems far older and far more beautiful than anything we've built. The systems that keep your heart beating and your lungs filling and your body warm in the dark. Let the loop rest. Let the sensors quiet. Let the motors stop. And let yourself, gently, without any corrections at all, fall asleep.